Essas aqui são do laboratório, eles só têm escolha. Bom dia. Good morning, everyone. I was starting in Portuguese because we used to use this language here in Sao Paulo. But since the course is international, we need to be using English. So welcome, everyone. I hope the system online is working and you can hear me very well all around. Thank you very much to be coming to this winter school. Organized by AUCANI, International Office of University of Sao Paulo, in collaboration with Faculty of Pharmaceutical Sciences of University of Sao Paulo. And idea of this course is present some information about the fermented food products. We will touch some biomolecular tools, how we can use biomolecular methods for identification and study of different processes going in the fermented food products. And with some examples of applications. So in next 5 days, we're going to have different lectures. It's about 30 hours lecturing, and we're having about 28 presenters from different countries, from New Zealand, Malaysia, from Russia, Ukraine, from United States, here from Brazil. Maybe I'm missing some of the presenters from Bulgaria. So the program will be more or less from 9 o'clock in the morning every day till 4 o'clock in the afternoon. And in the last hour, we're going to have some discussion of the lectures during the day, including some information about University of Sao Paulo, our different programs that we have for the post-graduation, our food research center as well. So with the presenters from all these services to give you information and including how you can actually apply and do your master or PhD at University of Sao Paulo and Faculty of Pharmaceutical Sciences. So today I will start myself, first presentation. My name is Svetoslav Todorov. I'm a professor at University of Sao Paulo, Faculty of Pharmaceutical Sciences, but my passport is Bulgarian. But since 16 years, I'm here in Sao Paulo. As they say, once enter in the house, I don't want to go out. And going to present about beneficial properties of fermented food products and how we can use these fermented food products as a source of beneficial microorganisms. My PhD, I have my studies in Bulgaria at University of Sofia, then PhD in France, University of Nantes, then work shortly in South Africa for almost 6 years, and then moved to Brazil. So let's start. I was giving some short description of my graduation and where I was working before. So let's go to the where in the moment we are. Okay. It's not moving. We have a small technical problem, but we can fix it now. And now it's supposed to work. No, it's not working. Okay. Yeah. Okay. Well, first, as I mentioned, I work for the University of Sao Paulo, and Sao Paulo it's one of the biggest cities in Brazil. So the Brazil is a very nice country, especially for the foreigners when they come here, because you can explore a very vibrant culture of Brazil from the south that is extremely European style and go north to the Amazon. So you can get all these options of the nature and the cultures and very vibrant mixed culture of all that you can imagine in this continent. University of Sao Paulo, it's a state university of Sao Paulo, and it's having several campuses all around the state of Sao Paulo. So it's not only one. We're not only in Sao Paulo city, but we have campuses in Santos, in Lorena, in São Carlos, in Ribeirão Preto, Pirassununga, Bauru, Piracicaba, so all around our state. And sometimes these places are quite far away one of each other, but it's important because all of them is under the umbrella of the same university and working all together. Well, our department and Faculty of Pharmaceutical Sciences are located in the capital of the state of Sao Paulo, in Sao Paulo, as we say, capital campus. Well, this is the one of the landmarks inside our campus. However, this is not our department. This is the Museum of Ipiranga that is part of our university. And our university, it's located our department is located in this building. Maybe it's not as beautiful as Museum of Ipiranga, but at the same time, it's one of the most producing laboratories and in our faculty. In my time, my work, I have several research collaborations with different universities all around the world. And this is actually an important thing because only based on the international collaboration, you can make your progress. But now let's go and talk about lactic acid bacteria and their application. Lactic acid bacteria have different applications, not only in the medicine, in the food and feed industry, in the chemistry, but as well they're much more important because they're producing different functional ingredients. And these functional ingredients can be associated with the production of different enzymes, vitamins, sweeteners, exopolysaccharides. Several of these lactic acid bacteria could be a probiotic. They have their probiotic properties. Their functional properties as a starter culture, it's very important because they have their application in dairy and not dairy industry. But as well, something that is more interesting for me, it's a production of the GABA and different antioxidants by the lactic acid bacteria. They have the very important application for the, not only for the health and in the food industry. As well, antimicrobial properties, production of these antimicrobials by the lactic acid bacteria is a very interesting point because they're having their application in the food industry, but as a biopreservatives, but as well they have their application in the medical sector. If we think about the different lactic acid bacteria, I don't need to convince you that they have their application as a beneficial and probiotic properties. They can be involved in the control of different disease, and as well we need to think about that the probiotics was not a medicine, they're supplements. They're something that can improve the effect of the Western medicine, but as well their properties and their strong effect on the health need to be clearly acknowledged. When we select the different lactic acid bacteria as applications, as functional properties and application in their benefits, we need to think about several options that we need to be sure. First of all, lactic acid bacteria need to have a good survival in our gastrointestinal tract because when we take them as a probiotic, they need to go via our gastrointestinal tract and they need to survive. If they not can survive, obviously they cannot have their beneficial properties. In the beginning, when the probiotics was selected, always been acknowledged and showed that they need to be human origin. Because if we take something from the human, we can introduce it back to the human and they most probably will survive better. But these days we have several evidences to believe that lactic acid bacteria from the fermented food products, from the animal origin, from the environmental origin, they can be as well applied as probiotics because they can have a good survival. They can bring these beneficial properties to the host. As well, production of the antimicrobial substances. Very often in the literature, it's a kind of wrong idea that production of the antimicrobials needs to be compulsory, obligatory, very important part for the probiotic properties. It's not needed. Production of the antimicrobials is just supplement benefits for the probiotics. That could be a good point. But if they don't have this production of antimicrobials, it's not don't mean that they are not probiotics. Because let's think about you having the probiotics that can stimulate immune system. So they don't need to be a producer of antimicrobials because they can stimulate immune system. They can give their properties. Probiotics then can destroy aflatoxin. They can destroy. They can take away heavy metals from our body. So these probiotics don't need to produce the antimicrobials. But when we talk about the probiotics that we want to be effective against some pathogens, antimicrobial properties are getting very important. And in this case, we need to be sure that they will have this because these properties, antimicrobial properties, because only in this way they will be able to remove some of the pathogens part of the that come to our gut. Coming to another, some of the other properties, addition to the intestinal cells. Well, if we think about the properties that are associated with the production of stimulation of the immune system, we want this microorganism to stay and be there in our gastrointestinal part. So in this case, a good addition, it's a very important because this microorganism needs to feel like in home, as a house when go in our gastrointestinal tract, and they can do their job there very well. However, if we think about different properties, such as I already mentioned, the removal of the heavy metals from our body, imagine you work in the mining industry, so you're exposed to the heavy metals all the time. And you most probably will charge your body with the heavy metals because of the environment the way you're working. So in this case, addition to the gastrointestinal tract to cells there, it's not a very good idea because probiotic needs to go via our mouth, needs to absorb the heavy metals and then very quickly go out. So this kind of idea for the properties adherence to the gastrointestinal tract depends on what we target with these probiotic cells. Okay, presence of the human persistence in the human intestinal tract. Again, same thing related with the fact what we want of the probiotic, what we target this probiotic to do for us. Another very important point is antibiotic resistance. Everyone normally screaming very loud when we talk about antibiotic resistance because we know, everyone know what's mean antibiotic resistance as a problem in the medical environment. Everyone know about vancomycin resistance, enterococci, methicillin resistance, staphylococcus aureus, and all this is a big problem because this microorganism is very difficult to be eliminated in the medical settings. However, probiotics need to be resistant to antibiotic or need to be sensitive to the antibiotic. It's a very good question because from one side, if we introduce the microorganism that is resistant to antibiotic, if this microorganism carry antibiotic resistance genes, these genes could be transformed to the other microorganism via the horizontal gene transfer. And this could be a very bad point because you can actually generate antibiotic resistance inside the pathogenic microorganism. There are several examples that lactic acid bacteria can transfer antibiotic-resistant genes to the pathogenic bacteria. But from another side, think about if you are, okay, let me put in the different way. We have several people online, but we have people in the audience here, and I will interact with the people in the audience because it's difficult, this one that is online. How of you are taking probiotic in these days on the regular basis? Just move the hands. Look like no one taking probiotics. Okay. But how of you will consider take a probiotic if you are sick to help you? Well, like more or less more than half actually. So it's coming this point. If you are in healthy status, you most probably you don't going to take a probiotic because, well, why spend my money? Why to charge my body with something extra? But if you are sick, you're going to consider to take a probiotic together with an antibiotic most probably. But taking probiotic and antibiotic, what will happen in your body? Obviously, antibiotic will kill the probiotic. So moderate the resistance to some antibiotics actually could be a good point because in this way you can take together antibiotic for treatment of infectious disease together with a probiotic that can help to improve your health status. So this is the point. What we understand by moderate antibiotic resistance. So this need to be antibiotic resistant that can be intrinsic, or could be maybe not associated with easily transformed genetic material. So if the antibiotic resistant gene is associated with the chromosome, that will be much more difficult to be transformed from one to another bacteria. So in this case, some very moderate antibiotic resistance could be considered as a positive point when we select new probiotic strains. But this is a point that is still open and not really having consensus in the scientific community, because we have some pro and against arguments for this point. So coming to the antimicrobial compounds produced by the lactic acid bacteria, not only by the lactic acid bacteria. This could be different: organic acid, diacetyl, hydrogen peroxide, carbon dioxide, bacteriocin, low molecular antimicrobials, and all these antimicrobials been applied by human society for the centuries, for the millennium. Because since people start producing fermented food products, these civilizations already in fact start to use these antimicrobials in their processes, even without having idea what is the acid, having no idea what is the bacteriocin, but they was using. Later, with development of the microbiological sciences, chemical sciences, we know that these metabolites are produced by the microorganisms, and we know that they have their beneficial properties. If you think diacetyl, it's a very common metabolite produced by lactococci normally, having this specific smell of butter, that is giving positive characteristic for the dairy products. But in the same time, diacetyl have the antimicrobial properties in the beginning of 20th century been even applied for the treatment of tuberculosis. These days we have a more sophisticated way for this treat this disease. But again, this antimicrobial property of diacetyl was quite important because they can improve the microbiological quality of the different food products. But since I'm interested in bacteriocins, I will give much more focus on them. By definition, bacteriocins are produced by not only by lactic acid bacteria, but several microorganisms, and they're produced by ribosomal machinery of the microorganisms. Well, but you can say, but all the proteins are produced by the ribosomal machinery of the microorganisms. Yes, it's true. But if you think this is the primary metabolite, they're having their gene organization, they can be produced, expressed, and just small modification after that, most probably losing a part of the leader peptide, so they can be activated and they can do their job. Argument will be, but yes, we have some antibiotics there with the protein nature. Yes, but they're secondary metabolites because they are produced. Then they have some modification in the cytoplasm of the microorganism. Because of this modification, they become active molecules. Normally, they're active against closely related microorganisms, but as well, in the last maybe 2-3 decades, we have some evidences to believe that some of the bacteriocins can have activity against some viruses, against Mycobacterium, against some gram-negative, well, produced by gram-positive, active against gram-negative. And as well, some of them could be even involved in more processes. It's important to underline that the bacteriocins normally are active against closely related. This was original definition. It's bacteriocin produced by lactic acid bacteria that are gram-positive. Normally, they will they can inhibit the other gram-positive. So they can kill their cousins, their relatives, but not far distant related microorganism. But this, as I say, needs to be discussed and needs to be changed most probably, because we have several evidences that work even against not closely related. As well, I like some of the presented figure from Mike Chikindas, that he was actually showing another opinion about bacteriocins. Look like they're not simple killers. They're not just killing molecules, because some of them can have much more complex effect on from ecological point of view. Some of them are involved in the cross-talking, in the quorum sensing, quorum catching processes. And this is the way this small molecule actually help in the communication between the bacterial species. Some of them could be really killing. They can, some inhibit, some can kill the other microorganisms. But interesting, when you go in the higher concentration, some of the bacteriocins actually can have effect on the eukaryotic cells. Some of them can have even effect on the cancer cells, inhibiting specifically very selective cancer cells and not healthy cells. And as well, some of them can even be applied as a contraceptive. And some examples will be provided on this direction. It is interesting to mention that the first bacteriocins been reported like almost a century ago. In 1925, first one produced by Escherichia coli, colicins. Later in 1928, first from lactic acid bacteria. 1933, discovery of nisin, that is authorized in the application in several countries all around the world, even produced commercially as a nisaplin, and having application in the not only in the biopreservation these days as a way of preservation of especially cheeses and some fruits and eggs, but as well in the last 2 decades, application in the medical sector, even for treatment of tuberculosis. As well, nisin was approved for several countries all around the world, approved by the European regulation and in the US. And as well, you can see in this figure that growing interest is about application of bacteriocins in the medical sector as well. And this is the number of the publication that I mentioned in the figure. And some and more papers coming related to how we can use the bacteriocin as a complementary treatment for some bacterial diseases, even as I mentioned, some cancer. Well, antimicrobial produced by the lactic acid bacteria, as I mentioned, they are different. They are a large spectrum of metabolites. But these metabolites can be used in the treatment of Mycobacterium tuberculosis. They can be treated as antiviral factors. Some of them can be bacteriocins. So we have some evidences to believe some bacteriocins can interfere with the development of herpes virus, with poliovirus. But as well, some of the lactic acid bacteria can produce proteinase inhibitors. And proteinase inhibitors was one of the important way to treat some viral infections, including some of the medicaments for the HIV control of the virus based on protease inhibitors, not from lactic acid bacteria, different nature, but this is a protease inhibitors. Some antifungal activity of lactic acid bacteria, and some antibacterial properties when they include all previously mentioned metabolites. As promised, I will talk about this non-specific action of lactic acid bacteria, and some of them coming from different products. In these slides, we have some effect of some of bacteriocins produced by different lactic acid bacteria isolated from boza, from coconuts, from salami. And all of them, how they can inhibit the growth of Mycobacterium tuberculosis. It's interesting to see that some of them, they don't have effect. We don't have panacea. We don't have something that will kill everything. But you can see that one of the strains, ST69BZ, strain of Lactobacillus plantarum, isolated from Buza. Buza is a Bulgarian, actually Balkan Peninsula cereal-based beverage that people from the Balkan Peninsula like it. When you offer this drink to people from the other area of the world, they say, no, it's disgusting. But you need to be used to the products. Well, I can say something for some of Brazilian products. I don't like Brazilian but this is typical things for what you grow with, what you like it. But again, it's interesting to mention that this beverage is used by traditional medicine for control of some of the influenza, even was used as a complementary treatment for the people from tuberculosis. Obviously, now we know that this beverage contains several lactic acid bacteria and yeast, and some of them can produce the antimicrobials that can have this effect against, not only against Mycobacterium, but several pathogens. Even we have to try and see that some of these bacteriocins can inhibit some viruses. So we now know what is why this traditional beverage is actually having these antimicrobial and beneficial properties. Well, it's interesting to mention that some colleague from Ireland, they was doing modification of the existing bacteriocin by modifying some specific amino acids. This is the group of Paul Cotter in Ireland. And in this way, they was able to have a very good inhibition of some Mycobacterium. And they was actually going in the direction to develop some new medicines for treatment of tuberculosis. In these slides, we have some effect of bacteriocin produced by lactic acid bacteria coming from, one is from, actually the two of them is from smoked salmon. And there was with good activity against some gram-negative microorganisms like Escherichia coli or Pseudomonas aeruginosa. And this is a good example of the bacteriocin that can kill a non-closely related microorganism. It is important to mention that very often we are going in the very interesting error, because when we use the semi-purified to crude extract to test the bacteriocin activity, we have residues from the growth media. And very often this residue from the growth media can have a facilitating effect of the bacteriocins, because we know the surfactants together with bacteriocins can be responsible for killing the gram-negative because it's facilitating their mode of action. But in this case, we was using bacteriocin that was purified. So we have pure bacteriocin, we don't have surfactants, we don't have residue from the growth media. So we know that bacteriocin himself is responsible for this mode of action against gram-negatives. Activity of some bacteriocins against viruses. In this case, we have the bacteriocin produced by Enterococcus munti, and this bacteriocin was able to inhibit 99.99% of development of herpes virus. We're having the 95% reduction of measles virus, or 50% reduction of polio virus. Well, I'm a microbiologist, I'm not virologist, and this result, 50%, for me sounds very like, wow, it's disappointing. It's very low. It's not low, because this work is done in collaboration with the University of Buenos Aires, and the colleague from university, she is virologist from University of Buenos Aires, Monica Vashman, she was explaining that in the area of the virology, 50% is considered a very good result. Obviously, we don't want to have the medicines against the viruses. We want a supplementary treatment. And you know that the poliovirus, it's a virus that affecting not only the life of the child, because it could paralyze the child and forever, but as well destroy the life of the parents as well, because don't even want to imagine if you have such a child at home, it means you need to take care for this child forever, even when he's adult. You cannot leave it. There's no way, there's no cure of this disease. And the bad news, this poliovirus is coming back actually in Latin America in the last years, and more cases. We have the vaccine, and this is the point to mention again, please use the vaccine. When you have the vaccine for some diseases, the best way for protection is the vaccine, and not look after that for the cure of the disease. Well, some people are anti-vaxxers, but they said their problem. I'm pro-vaccines. Interesting point, we have evidences to know how this bacteriocin work actually against viruses. And again, colleague Monica Vashman from University of Buenos Aires, she was showing that actually presence of the bacteriocin is blocking synthesis of the gamma peptide of the reconstruction of the virus. So virus cannot be reconstructed because it's missing one peptide. And since this peptide is missing, virus cannot reconstruct, and you actually stop the virus infection. During the COVID pandemic, we tried to see if we can use some of our bacteriocin against COVID virus, but that was not working. But again, we don't have panacea. We don't have bacteriocin that can do all the jobs. So we need to just to find appropriate microorganisms with appropriate bacteriocin that can do the work, or protease inhibitors. In this example, so we have some options to show that some of the lactic acid bacteria actually can inhibit the fungus. Well, in this case, it's not a bacteriocin, it's a bacteria himself. But again, we can control Aspergillus, Penicillium, Epicoccus, fungal development by some microorganisms. And again, you can see some of the lactic acid bacteria applied in these experiments can work, some not. Again, very interesting that this one that I mentioned, that with the good antimicrobial activity, Lactobacillus plantarum ST69 coming from Boza, as well having some good effect on the inhibition of some of the fungal infection. However, we wanted to know more how this work, why this work. And we're having this work performed a couple of years ago, 3 years ago, with one of my master students in Korea, Ivy Fugaban, and she was exploring the antifungal activity of several lactic acid bacteria, especially Enterococcus faecium and Leuconostoc citrum and Leuconostoc mesenteroides, strains isolated from different origin, and strains that was coming from traditional Korean products, different soy-based fermented paste. And interestingly, some of these strains was showing very good activity against some of the fungal including some of the bacteriocins was showing good activity. But we wanted to know what's actually going. This is the reason why we performed the metabolomic analysis of the supernatant of when these strains grow. We wanted to see what's going, which metabolite actually is much more present, which metabolite maybe could be associated with this antifungal activity. Well, we was expecting that this will be most probably phenylactic acid, because this is the acid that was reported in the literature as a predominant antifungal metabolite produced by the lactic acid bacteria. But our surprise was not. It's not phenylactic acid. In fact, it was all other different metabolites shown in green in this table, that their presence in fact was responsible. So then we made a combination of all these metabolites as a pure chemical metabolites, not coming from the bacteria, just buying them from supplier. And we was checking, and it was interesting to see that as a single metabolite that was having much more less activity. But when then combine it in the proportion like in the real situation, that was having much more better antifungal activity against these metabolites. As well with Ivy Fugaben. By the way, she is in the moment PhD student in Denmark, and hope she will consider come for postdoc here, because was very productive as a student. She's from Philippines. We was investigating destruction of the biofilm formed by Listeria monocytogenes when we was using some of these bacteriocin with already saw that they're having antifungal activity, but we wanted to see how we can destroy biofilm formed by Listeria. And we was using the different methods. We was looking for live dead cells. We was using flow cytometry to see live damage and dead cells. And in this way, we was observing that these bacteriocins actually then can be applied for the destruction of the biofilm. Furthermore, we wanted even to see the combined effect between bacteriocins and some antibiotics. In this case, we was using ciprofloxacin and vancomycin to see how they can destroy Listeria monocytogenes, and as well observing some synergistic effect when we apply antibiotic and the bacteriocin. And this is the point that's showing that we can use the bacteriocins as a complementary, as an additional way to treat some of the infection diseases, and we can reduce the application of the antibiotics. In this case, we're having some example when you use the bacteriocin produced by Pediococcus pentosa cells, and together with ciprofloxacin, we was able to reduce the growth of Listeria. Interesting is that this strain is isolated from marula fruit. Do you know marula fruit? Someone been to South Africa? Okay, marula fruit, it's a fruit that the elephant eat and get drunk, because they ferment in their stomach and produce the alcohol. And marula fruit is used to make a kind of wine, then fermentation, of course, process. Then they do the distillation. They make a distill, concentrate alcohol. They mix with the cream, and they have a marula drink. So now it's no excuse for you to drink a marula and think that you will have the bacteria, because in marula, no live bacteria. But bacteria isolated from the fruit was actually very potent and a very good antimicrobial properties. And interestingly, we have this synergistic effect between this bacteriocin and ciprofloxacin in the control of Listeria. Well, but Paracelsus have a very good idea, and he said that everything in the nature is a poison. I mean, how many of you it's pharmaceutical degree students? Okay, not too many. Who is not pharmaceutical? Rest, obviously. But you know that not existing medication that is not poison. Technically, every medicament that we take, it's a poison. Okay, we need to take in the right concentration so they can benefits of the beneficial property of the medicament and the drug, and then don't have the wrong part. And it's obviously we need to know what's the toxical effect of the bacteriocins. Most of the bacteriocins are considered as a safe, because studies showing that niacin, most applied bacteriocin in the world, actually having the cytotoxic effect on almost 7 grams per kilo. That is more or less the cytotoxic effect of sodium chloride, cooking salt. Can you have this amount of bacteriocin in daily consumption? Practically it's impossible. I mean, it's enormous amount. We talk about pure bacteriocin, not semi-purified or whatever. So most of the bacteriocins, yes, they're completely safe. However, think about every bacteriocin have the different amino acid structure. This is a small proteins, polypeptide. And this amino acid structure can be different, can have the different cytotoxicity. So just because the niacin is not cytotoxic, we're not supposed to think that all the bacteriocins are not cytotoxic. All of them are different. Even you change one or two amino acids in the structure, you can change the cytotoxicity. But something that is interesting, some of them, in fact, could be a very interesting point if they are cytotoxic. By error, we actually discovered that some of our bacteriocins are very highly cytotoxic against cancer cell lines, but not cytotoxic against healthy cell line. And in this way, we can actually think about that we can use the bacteriocin with a high cytotoxicity against cancers as a treatment way to treat some cancers, because they will go target cancer cell line and they can actually destroy them, can kill them, but at the same time, they're not going to touch the healthy cell lines. So this is actually a very important point, because in this way, we can actually having a new application, medical application. And there's a paper published already quite a long time ago, showing that several bacteriocins can actually have these cytotoxic effects against some cancer cell lines. And they was actually suggesting that they can be applied in the control of some cancers. Well, in this paper, the author was not showing what is the effect on these bacteriocin against healthy cell lines, but we already have some evidences to believe and prove that these bacteriocin very often, they don't have effect on the healthy cell lines. So obviously, when we want to propose an effect against cancer cells, we need to be sure that we're not going to affect the healthy one. But this is just a question of the test. Then we're coming to another example of Lactobacillus plantarum isolated from Lactobacillus plantarum isolated from Bulgarian sausage called Speck. In German countries, it's different products by this name, but well, in Bulgaria, it's a kind of salami. And interestingly, this strain producing a very good bacteriocins with a very good activity, can kill several pathogens, so everything's okay. But again, we want to apply these strains in the production of the fermented food products. How we can apply it? Are we sure that the strain is safe? Very often people answer yes, but Lactobacillus plantarum is considered as a grass species. They are not a problematic. Yes, this is just a recommendation. And we need to be sure every time that this specific strains, it's safe as well, because species, strains are different things. Species could be considered as safe, but every strain needs to be evaluated on the individual basis. So we was checking for several virulence genes, antibiotic-resistant genes, and when we check for the presence of these genes, we found that only few of them are present in the genome of this strain. However, when we try to see expression of these genes, we was observing that some of them cannot express. So the gene is there, but several times the operon is not the same and not allow the gene to be expressed. So we can consider this strain as safe. And in the same time, we was having a different other strains, some of Lactobacillus saki or other plantarums that was showing a presence of much more virulent genes. Some of these strains as well, we evaluated for production of GABA. And GABA is associated with the several beneficial properties, and having effect of as an antidepressant, sedative, antihypertensive, can be associated with the control of the blood pressure, having even anti-diabetic properties, anti-cancer, immune system enhanced. And this is important because some of the lactic acid bacteria can be producer of GABA, and they could be actually enriching the fermented food products with the presence of this metabolite. It's something we're actually exploring in the moment in the laboratory, looking for the appropriate strains that could be producer of GABA. There's some example of strains that we isolated from different fermented food products, and we wanted to see if they can produce GABA and how we can actually reintroduce later this strain, enrich the fermented food products with this strain, and having enriched production of GABA. Coming back to another point of the fermented food products. As I mentioned in the beginning, I'm Bulgarian, and obviously I will do the advertising of my country. Countries located in the southeast of Europe, coming with a region with a very rich culture for more than 3,000 years, culture that is developed in parallel with the Greek cultures there, influenced by the Greek culture. And as well, the region is very rich of different fermented food products. Some of them are fermented food vegetables. And interestingly, we wanted to know if we can use these fermented food products as a source of lactic acid bacteria. So we collected some of them, and we was looking especially for the food products that are produced for the local consumption, for private consumption. So there is no chemicals, organic production, everything made it in the cleanest possible way. But interestingly, microbial load of this fermented food product was not very high. But if you think about sauerkraut, how many bacteria involved in the production of sauerkraut? It's one bacteria come, then it's coming another one. First one disappear, coming second one disappear, coming third is there. It's a very dynamic process of the fermented process. Same thing with the fermented vegetables. There are several microorganisms involved in their processes, and final microbial load is not very high. It's like 10 to 4, 10 to 5 CFU per ml. Interestingly, we have several microorganisms from the same batch of fermented food products. We had like 4 different Lactobacillus plantarum. We have one Lactobacillus curvatus, Lactobacillus paracasi, Pediococcus pentosa cells, Leuconostoc mesenteroides, Enterococcus faecium. And all of them, we was actually screening for bacteriocin producer. When we were doing the work, we wanted bacteriocin producer. We don't care for rest of the microorganisms. But interestingly, very rich variety of microorganisms present in this product. And all of them are different strains, because we proved this by the appropriate biochemical and biomolecular way to prove that this is really different strains. All of them producing antimicrobials, and they was having a good activity against several Listeria monocytogenes. They was giving different vancomycin resistance enterococci. They was not killing gram-negative well, but we don't have bacteriocin that can kill everything. And remember, according to the definition, they're supposed to kill only their cousins, they're closer related. So no activity against gram-negative is not end of the world. Interestingly, very low activity against another different lactic acid bacteria. Some of them that we use as a test microorganisms is actually probiotic strains, so it's a good point, because you don't want to kill the good bacteria. You want to kill only bad. And vancomycin resistance are a big problem, vancomycin resistant enterococci, and as well Listeria. I always want to kill Listeria monocytogenes. I'm not going to tell why, but most of people already know that it's a bad bacteria, and especially for the immunocompromised, for the old people, for the small child, for the mother-in-law. And then we wanted to see if these strains are safe. So we checked them for the antibiotic resistance, and it's important when you do the antibiotic resistance to respect the EFSA recommendation, because we're not checking antibiotic resistance what we have in the lab. We need to check what EFSA recommend for each bacterial group against which antibiotic we need to evaluate, because this is important, because this way we can see if really strain is safe or not. Then we check hemolytic activity, gelatinous activity, production of biogenic amine and mucus degradation properties. And we was actually quite happy, because our strains were showing a very reasonable, not excess antibiotic resistance, just for the few antibiotics. So as I mentioned in the beginning, we need to consider this as actually an option in good selection criteria, because we can suggest later them to be applied with together probiotic and antibiotics. Vancomycin resistance, so we need to mention that it's a problem in the enterococci, but in the lactobacilli it's intrinsic, so it's will be always there, so it's not surprising. And then we wanted to see how these strains actually can survive in the gastrointestinal tract. And they were showing a good survival. It means they can go with the mouth, they can go in the stomach, low pH cannot affect them drastically. They can go in the lower part in the gastrointestinal tract, they can survive there, and they can actually do their job. Because if you have the dead bacteria, what's the point? It cannot be a probiotic. Now it's coming to another point. We can have the postbiotic. But it's a different story, because in the case of the postbiotics, we are applying the dead cells. We kill them and we apply them together as a part of the dead cells, metabolite and everything, but this is a completely different story. When we have a probiotic, need to be live and need to be appropriate number. Then we wanted to know how the hydrophobicity of this bacteria, it's which level they have, because hydrophobicity is actually giving us information how this bacteria can actually go and adhere to our gastrointestinal tract, because we already know that the hydrophobicity have the like parallel relation with the addition properties, and it's much more easy to do the hydrophobicity than do the cell line experiment to see how they adhere. So you can actually pre-select the strain that are having good adherence, and you can go further and evaluate them in the other model system. But as well, we was interested about the antioxidant properties of these strains, because antioxidants, we can have it by different fruits, we can have it by bacteria, we can have them as a chemical additives. Obviously, I prefer the fruits or fermented food products, not the chemical additives, but sometimes we don't have choice. But again, if we can have a bacterial strains with the good antioxidant properties, this could be a very good option, because we can reach the same goal using our fermented food products. So we was evaluating different options for antioxidant properties for these strains, and we was checking and see that can really work. Some of them was having very close to control levels. We checked the ferric-ion chalating activity. We was checking for hydroxyl radical scavenging activity. Some of them was almost like a control. Some of them was lower. But again, we cannot expect same strain to do everything. Some of them in the superoxide anion radical scavenging activity was showing almost the same effect as a control, or even the lipid peroxide inhibitory rate. Some of our strains was even better, performing better than control. So in conclusion, these strains isolated from Bulgarian fermented vegetables, they was producing bacteriocin that can be considered as safe strains. They have their antioxidant property. They can have a good potential to be applied as a probiotic. Because of course, we need to do appropriate animal studies, in situ evaluation, even to be validated them as a probiotic. We need to go for appropriate human trials and validation of this. But this is a good point, because we can have all these fermented food products, including these fermented vegetables from Bulgaria, and not only from Bulgaria, all around the world. You can find the different fermented food products rich of antimicrobial producing lactic acid bacteria with several beneficial properties, and you can enjoy the good food, and at one time you can have the benefits of this microorganism and produced by them antimicrobials and beneficial metabolites. As well, we was evaluating some cheeses and showing that during the fermentation of the cheeses, we can actually produce several bioactive peptides. So this is a good point, because again, we're explaining why the dairy products actually can be considered as a beneficial products and recommended by traditional medicine for the centuries. Actually, we can know what actually going, what is produced, how it's produced, and how these products can be applied. As well, production of the vitamins by some of the lactic acid bacteria from different origins. In this case, we have the several lactic acid bacteria isolated from the milk, fermented and non-fermented milk, and they can produce folate during their growth, and even was showing in the animal model that this can work very well. And as well, something that I think I need to mention, we're having this suggestion for the standardized abbreviation of the lactic acid bacteria. Since 2020, we're having a change in the taxonomy of the lactic acid bacteria, and it's become a big mess when we write a paper this day. Because before was very easy. Lactobacillus, LB or L, we abbreviate. This day, Lactobacillus, it's split in 25 different genera. So we need to find a way that we can actually abbreviate them in the different way. And we had this suggestion that we can standardize abbreviation by 3 or 2 letters in order to know which actually new species, a new genera we're talking about. As well, going to use the opportunity to remind you that end of this year will be a conference in Brazil, in Santos, in the middle of November. It's every 2 years, International Association for Food Protection organizing ASCO, International Association for Food Protection Latino Conference. And this year we'll be here in Brazil, in Santos. So till end of this month, you still have time to submit your abstract and plan your trip to Santos in November this year. And the program is quite exciting with the presenters from all around Latin America, Europe, US, Asia. As well, next year in March will be a conference fully sponsored by Yakult, Brazil. And this conference will be giving a focus on different beneficial properties of lactic acid bacteria. And I hope as well you can put it in your agenda and maybe planning to attend this conference. And in the end, just don't want to be afraid to be innovative and creative, because just remember the Ark of Noah was built by only one person that never had engineering degree, but who was supervisor. It means supervisor is very important. And Titanic and Costa Concordia have been built by the professional people, but you know what's happened with both of them. Just go down to the bottom of the sea. So thank you very much for your attention, and thank you very much for all my collaboration in the last almost 30 years from all around the world, starting from New Zealand and going via Asia, Europe, Africa, Rutgers University from North America, and all the collaborators from Latin America and Brazil. So thank you very much. And if you have a question, this will be the next part of this session. Questions from the YouTube, I think you can write on the YouTube, and we're going to transmit here. And the next presenter is almost ready, but he will be giving him time in 10 minutes. So if you have a question, now it's the time. I have a question. People in the audience who work with the lactic acid bacteria. Only one, two, three. Who consider to work with the lactic acid bacteria? Only one. Already good. Wellington, maybe you can check on the system what the theory is. Well, since this is a YouTube presentation, the presentation will be available for certain time according to the regulation of the university. Slides not going to be provided. I mean, they have copyright of the authors. But the presentation will be available for I think it's normally 1 month that the university keep them online, or is it? Well, at the moment, they will be available for the short time. Later, maybe we can have the authorization for the authors, and all the YouTube presentations will be available for a little bit longer time. But again, this winter course was sponsored by Alcani of the University of Sao Paulo in collaboration with the Faculty of Pharmaceutical Sciences of Sao Paulo and Faculty of Pharmaceutical Sciences in campus of Ribeirão Preto of Sao Paulo University. So it's for free, and its idea is to distribute this knowledge for free. So we have more or less almost 400 subscribe on the course. This morning was 385, I think. So again, we're going to see if it's possible to have authorization from all the authors and keep them for a little bit longer time.
There is a question from the audience. I will not pronounce this name. I want to ask I want to ask that, do you think about possibility of conservation of fresh fruits and vegetables by LAB for purpose of prolongation of their storage time?
Well, some of the lactic acid bacteria actually having this application, and some of the metabolites, they use them for the treatment of the fruits when they export, especially from the other countries. Because you know very well, especially tropical fruits, they are collected, they need to pass very long time to arrive to the place. So they already use them. It's something that is already applied. Very often this is some metabolites, or not very often lactic acid bacteria, because bacteria himself could be a problem, because could be considered as a spoilage, but some of the metabolites, they're already in the application. So if you don't have more questions, yeah, there's a question here from the audience.
Okay. Hello, good morning, everyone. I'm Adamu from Paja University, Visosa, Minijerice. Well, my question here is, like in my country, Nigeria, like we have a lot of fermented foods, and like meat and milk, and that process is undergone on controls. Is there any maybe health effects, maybe for the women, such Africans, or maybe an old age people, maybe a long-term effect?
Well, I was working for almost 6 years in South Africa, so having some experience in the African continent. And this area, it's a very rich of fermented food products. It's an enormous variety and quality of fermented, especially fruit, vegetables, cereals, meat products, not too many dairy products, but several other. Interestingly, very often this product was made by natural spontaneous fermentation process. And we was actually having worked together with the University of Harare in Zimbabwe. We took a Massey and we explore why a Massey actually having such a long shelf life. And we was actually amazed to see that several lactic acid bacteria are part of the fermentation process of a Massey. It's a dairy products, fermented dairy products. And with most of them was actually producing antimicrobials. And this is explaining what's going there. From the other side, it's very interesting and important to study these products, because very often these products are produced by the traditional way. There was not really very well know exactly what's going there, because very often they're produced in very small scale. But as well, in the literature, coming more and more articles coming, especially from the Central Africa, showing different traditional products, what microorganisms are involved, how this microorganism actually conduct fermentation process, what's their role, which acids are produced, which antimicrobial produced. It is getting more and more interesting, because some of these microorganisms having much more potential, not just a starter culture, not only biopreservative culture of this product, but they're extremely rich source of the knowledge and the new antimicrobials, with very good applications in another sector, especially in the pharmaceutical and biopreservation sector. So this is something that is going, and it's very important, because in this way we can select new strains for the future fermentation processes applications. I think we need to have a small break now, because the next presenter will need to start in a few minutes. So please, the technical staff, you can play the advertising video.
Thank you.
And then we can continue in a few minutes with the next presentation. Morning, Juliano.
Morning.
Okay, next speaker, it's directly from Florianopolis. It's Juliano Lindner. He's a professor at University of Santa Catarina. And it's a very good pleasure to have you here today with us because really respecting your work in the lactic acid bacteria and their technological suitability in the food products. Because as a microbiologist, I like to isolate the new microorganisms, but then you need to apply them in the food products. So it's a work together. So Juliano, I will really appreciate if you can give a few words about you in the beginning, and then you have your time to present your work. Thank you very much for accepting our invitation. And now it's Utah.
Thank you, Professor Todorov. Do you listen me? The sound's okay? Yes, okay. Good morning. Thank you, Professor Todorov, to invite me for this winter school. For me, it's a pleasure. Now I'm a professor in the Federal University of Santa Catarina in the Department of Food Science and Technology. And the title of my presentation is Technological Suitability of Microbial Cultures for Food Application. Let's start. Let me see, how can I pass this slide? Okay. This is our slide plan. We will start my presentation talking about a little bit history and interactions concerning the technology, microorganisms, and raw materials in a food fermentation. After that, we will talk about lactic acid bacteria, the inventory of microorganisms, safety microorganisms, and the identification and culture analysis of these cultures, and classification and technological aptitude, the functionality of these cultures in a product. And after that, show to you some studies executed here in the Federal University of Santa Catarina. And to conclude my presentation, I will show to you what I think that is the future in this field. So, as a premise of my presentation, I want to talk a little bit about this history in this region of the globe, the Caucasus, the Caucasus Mountains. We empirically developed two close products called kefir and yogurt, famous products. The little difference about these two products is because kefir was empirically produced in the North Valley of these mountains using a mesophilic microbiota. And the yogurt, on the other part of the mountain, was developed using a thermophilic microbiota. This is the quite different about these two products so closely related. Together with this, the consumption of these two products by this population in this area, together with the domestication of animals, the human population, the gene of the lactase will diffuse it in the human population. The human, in the late phase of the life, starts to drink milk and dairy products, and this develop this situation, this genetic variation of the part of this population will be diffused in the population. A little bit of this history can be read in this Jared Diamond book called Guns, Germs, and Steel. After that, so close to the nowadays, in 1908, Eli Metnikov, this Russian biologist, created an hypothesis that the species of bacteria present in yogurt positively influence health and positively influence the longevity of the Bulgarian and Caucasian shepherds that consume yogurt in the yogurt and milk in the late phase of their life. So, in this time of the human, in the science of the human size, for the first time, we have this name for microbial cultures. Nowadays, fermented foods are a huge market and corresponding to 40% of the market, of the food market, according to the Innova database. And the bacteria and fungi, the metabolites of the bacteria and fungi and the process to produce this, a lot of quality products, like, for example, yogurt, cheese, wine, etc., can be produced by this type of microorganisms. And in my opinion, the knowledge and the experience, the professionals of the food industry need knowledge, a huge knowledge and experience, and together with the safety and quality of the raw material and the products, this association can generate economical vitality for the food industry. And in looking for these numbers, we can understand that the market don't stop to grow. The market and the products don't stop to grow. So, to convert raw material in a good quality food, fermented food, we need a deeply understand of the biochemical modifications associated with the metabolic activity of bacteria and fungi. I like to think in the association of raw material, the process and the technology, together with the safety microorganisms as a triad: raw material, technology, and microorganisms. And the other important thing connected to this triad previously shown in the previous slide, for obtaining a high quality fermented food, is understanding the ecological process that drive the microorganisms to the matrix, and the microbial community succession involved in the ripening. Biotic and abiotic factors. Do you see my mouse pointer? No? Okay. No problem. The biotic and abiotic factors generate pressures during the ripening on the organisms, conducting to different biochemisms on the food matrix. But now we can start to see more about the bacterial cultures and the growth of and the group of lab, as showed by Professor Todorov in the previous presentation, the lacticase bacteria group. For me, the really protagonists of the food fermentations. This bacterial group, can be considered as starter. The starter lacticase bacteria are intentionally added to the process, and the not starter lacticase bacteria came from the environmental and from the raw milk, in this case, looking for this nice product called Parmigiano Reggiano, and altogether these microorganisms conduct the process to produce this nice product. Together with the proteolysis and lipolysis and other metabolic pathways, we can have a good product, fermented product. Okay, but how can we understand which species can be considered a microbial culture? For sure, microbial culture for use in fermentation process. We can start with this first question. How can we understand which species can be considered? So we can start looking for the history of safe use. History of safe use, can be structured by this synonym, where significant human consumption of food or cultures viable in this food over several generations and in large scale consumed by a diverse population for which there exists adequate allergenic and toxicological data to provide reasonable certainty that no harm will result from the consumption of this food. We can start with this definition. This definition provided by the Health Canada. This definition, together with evidence that the use of these cultures in the product is beneficial, can conduct to the start point to understand if a culture is safe for application in a food. In this slide, you can show, we can see this paper that brings together with the definition, inclusion and exclusion criteria. After that, we can see, for example, the European Food and Fermentation Culture Association, the EFCA, published a document, recommended guidelines to assess the safety and characterization of a food culture. And using a decision tree, the EFCA defined the five steps to understand better if a culture can be used as safe culture can be used in a product. The first one is the identification of the culture. The second one is the antimicrobial tests for antimicrobial susceptibility. The presence of these species in a qualified presumption of safety status list, tests for production of antimicrobials, and pathogenity and toxicity situation for the culture. The EFSA, European Food Safety Authority, every 6 months update the list of the qualified presumption of safety microorganisms, qualifying the microorganisms for application, and before receive a market authorization. So the presence of the speech in the list for a status of QPS, therefore, does not guarantee market authorization. In this next slide, we can see in 2017 the practical examples of assessment for novel microbes for human consumption. The presence in the list of the KPS needs to, after that, an assessment for the EFSA to obtain the green flag to the using in a food product. In this review paper, we can see the practical examples for these 4 microorganisms. Continuing this situation, we can observe for this new issue, the International Dairy Federation, the IDF, published in 2022 an update bulletin for the inventory of microbial food cultures with safety demonstration in fermented food products. At that time, 325 species were declared as a safety from different food sources. So, after understanding what can be considered a microbial culture, like species, and knowing that the microbial ecology of fermented foods is complex, we can associate traditional, contemporary, and modern microbial techniques to identify and analyze the microbial cultures using, respectively, culture-dependent, culture-independent, and omic techniques to understand this field, to better understand the field. With the advent of whole genome sequence, the WGS, the industrial microbiology had a huge development. So more understanding was obtained after the application of these modern technologies and the whole genome sequencing. So this is our second question in this presentation. After understand the presence of different species in different food products, we can make this second question. Why search for biotypes? Until now, we talk about species, and now we need to go ahead talking about biotypes. Why biotypes? The presence of individuals of the same species with different biosynthetic phenotypic activities is relevant for a food fermentation. This is relevant for a food fermentation. The search for biotypes, because these biotypes have biosynthetic phenotypic activities different. And this is so important in this part of a presentation. Biotypes in practice best adapt and colonize the food substrates. This can be observed in the theory of selection. These biotypes can impose themselves during different stages of fermentation because used in a different way different substrates and modify these substrates during the ripening. And the biotypes justify the great versatility of bacteria and represent an opportunity for the use of strains with greater technological functionality. This is so important for the industry of starter cultures. The search for functional different biotypes. Biotypes provide technological aptitude, or in other words, functionality. In just few sentences, this functionality can be obtained by the production of primary functional metabolites. These primary functional metabolites are so important for sensorial and structural characteristics of the food product. These biotypes can inhibit spoilage or pathogens bacteria, and this is an issue related to the conservation of the product. And these biotypes can produce other metabolites like secondary metabolites that impact on so important to impact the structure, flavor, and aroma the food product. And in so curious way, a biotype needs to autolyze itself. This is a nice thing, because after the autolysis, after the apoptosis of cellular apoptosis, the cell release a huge arsenal of intracellular enzymes that is so important for the proteolysis, the lipolysis, and for the ripening of the product. So a biotype needs to produce typical food, to produce food typicality. This search for this, when you produce a fermented food, we need to think a lot in the presence of characteristics that generate typicality for this product. The metabolism of these biotypes are regulated. This regulation can be positive or negative by inhibitory interactions with other microorganisms. This we can see by the Jameson's effect. The regulation, the metabolism of biotypes is regulated by the technological process parameters, by the production, the feedback, positive and negative feedback by the primary and secondary metabolisms, and the substrate modification during the ripening. For example, water activity, pH, etc. Okay. We can now pass for the second part of the presentation after understanding a little bit more about the microbial cultures, the safety of these microbial cultures. And now I can show to you related studies, 3 research lines involved technological suitability from microbial cultures. And this study was developed in my research group here in Brazil, in Florianopolis, in Federal University of Santa Catarina. First of all, I will show to you some studies, developed studies related to the search for optimized production of yogurt, a sheep's milk yogurt, with a high conjugated linoleic acid content. CLA, conjugated linoleic acid, is a functional molecule that you know, using food supplements associated to the health of the health. In this first work, produced during the PhD of the Gabriela Kuhl, we isolate more than we used more than 35 strains and screen their ability to produce CLA from LA in sheep's milk, to produce a high CLA content milk yogurt. After that, the best 2 strains that better convert linoleic acid in conjugated linoleic acid were used in a 11-run fractional factorial design to investigate the effect of 4 variables, in this case, glucose, powdered sheep milk, and LA. using a ratio of Streptococcus thermophilus and Lactobacillus bulgaricus in 1:2. After that, we observe highest levels of CLA, more than 42% produced, and this production in experimental, the production of CLA in experimental production was quite similar to the CLA predicted production by the polynomial quadratic developed model in this work. We was able to produce a functional yogurt with a high quantity of CLA in this work. After that, the best converter, the best producer biohydrogenator CLA, Lactobacillus debureki subspecie bulgaricus, biotype LBP UFSCI 2230, was sequenced, and the sequence was obtained to try to identify the enzymes involved in the CLA metabolism in this strain. The obtained draft genome for this strain represent an important tool to identify the enzymes involved and generate a better understanding the enzymes involved in this strain CLA metabolism. In this work, we identified the gene encoding an enzyme involved in the biohydrogenation of linoleic pathway. This enzyme was called oleate hydratase. After that, using the same strain, the same biotype, we constructed a recombinant strain of Lactobacillus bulgaricus, biotype UFSCI 2230, by overexpression of the putative enzyme oleate hydratase. The gene oleate was cloned in E. coli, expressed, purified, and characterized. This work was nice because we can understand that we can use this recombinant strain to convert, to optimize in an optimized substrate, to convert CLA production, for example, by a biotech industry. So the next line of research, we work with sourdough fermentation, massa madre, levain, sourdough, during the PhD of Leidiane Menezes. We start in a pioneering way in Brazil, studied using metataxonomic analysis, studying the sourdough, the production of sourdough from different Brazilian sourdoughs. And in this first work, we isolate more than 100 strains from the sourdough. The sourdoughs used in this work were propagated in two different temperatures, 21 and 30 Celsius degree. After this first work, we try to better understand the possibility of ferment a sourdough and reduce food maps in breads. In this first work, this production of sourdough was using endogenous microorganisms. What is food maps? Food maps is a fermentable oligo, DN monosaccharides and polyols that is present in vegetables, like for example, cereals, that is quickly fermented in the boil, in human boil, after the consumption of these products, and that are linked to two types of situations, human situations in patients. For example, with irritable bowel syndrome, IBS, and non-celiac gluten sensitivity, NCGS. The presence of these food maps in the food during the assimilation of the food can exacerbate the symptoms in this type of patients, in these pathogenic situations. In this work, we observed the reduction for all food maps produced with sourdough, that produce sourdough and then bread, and for the fructan, the total quantity of fructan, the reduction of more than 75%. After that, we try to another time conduct a reduction of food maps in the production of bread, but in this work, we try to do in a controlled way, using after the screening of the lab, producing a synthetic microbial community with these three combinations, microbial combinations, S1, 2, and 3, with different microorganisms isolated from the Brazilian sourdough. After that, we produce 3 types of sourdough, type 2 sourdough, and make the bread. So in this work, the bread presented lower concentration of food maps, a greater volume, and better performance during the shelf life, compared to the control bread produced only with baker's yeast. Baker's yeast Saccharomyces, in this case, Saccharomyces cerevisiae. The sourdough type 2 that we produced in this work allowed the reduction of fructans more than 90%. Thereby producing in a surprising way a good low food map bread that is suitable for IBS and NCGS patients. Our last work, recently published in Food Chemistry, during these studies with sourdough, we try to, using quantitative proteomics, exploit the impact of the production of sourdough and breads on reducing wheat allergenic fractions. In this work, we obtained 85 proteins. These proteins were identified as allergenic, mainly belonging to gliadin fraction, including 7 of them containing the famous 33-mer peptide sequence that is so associated with celiac syndrome. The highest relative abundance of allergenic proteins was found in the control sample, so the bread produced with baker's yeast. And the lowest presence of relative abundance of allergenic proteins were observed in sourdough. So we start the understanding that this type of fermentation can produce a bread with better characteristics to be consumed by a celiac patients, a low food map bread. The third line of research that I will show to you, we try to biodegrade the harmful compounds in meat. These works were produced by during the PhD of Luciano Molognoni and the masters of Gabriel Emiliano Mota. The International Association of Research on Cancer in 2015 readequate these three in red, in the slide in red, products, substance, nitrose compounds, heterocyclic aromatic amines, and polycyclic aromatic hydrocarbons, reclassified them in a worst list in the group 1 to carcinogenic substances to humans. But in an interesting way, the 1,4-dinitro-2-methylpyrrole, the molecular known DNMP, the acronym, call it DNMP, and the ethyl nitroic acid, the acronym ENA, were not present in the hierarchy list. These noxious compounds, for example, DNMP and ENA, can be formed by interactions among reactants in specific conditions in processed meat. For example, the interaction among nitrite and sorbate can produce, in certain conditions, the DNMP. So when we observe this, we will study this situation and know that for more than 40 years ago, anyone studied this DNMP and noxious compounds, and for us, this was a good opportunity to study this system, this biodegradation of these harmful compounds in meat. So, the first thing, we need to develop an analytical method. And in this paper, we developed this method using liquid chromatograph in tandem associated with mass spectrometry to develop an analytical method to assess the mutagen DNMP in meat products. After that, with analytical method developed, we assess the Brazilian situation for 20 different commercial samples, meat samples, to verify the presence of these mutagens, ENA and DNMP, in which nitrate and sorbic acid was used as preservatives and were previously detected in the matrix. For our surprise, 3 samples, one of mortadella bologna type, 1 chicken pate, and 1 bacon, we found it was possible to quantify these 2 carcinogenic compounds, ENA and DNMP. This was not a good news. We found a really important problem in some commercial samples of meat in Brazil, product meat in Brazil. After that, to show the power of the lactic bacteria to convert, I like to say that the lactic bacteria can do everything. Just you need to try, and we will be surprised with this group of bacteria. We try to bioconvert, degrade the DNMP using a process meat model. And in these two works published in these 2 different journals, we demonstrated the conversion of the DNMP in an anoxious molecule called NMAP in a different way by different lactase bacteria. And again, the Lactobacillus delbrueckii, subspecies bulgaricus, quickly transformed any nitro, C-nitro, and C-nitrose type mutagens in meat products, demonstrate the ability of quickly convert these carcinogenic substances in a meat model. Just to conclude my presentation, I want to show to you, in my opinion, what is the future for this field. The first future for me is the design of synthetic microbial communities, studying synecology. Synecology is a branch of the ecology that study the relation concerning about between the microorganisms, and in this case, this work published in this journal presented the principles for the design synthetic microbial communities, and for example, the use of the synthetic communities to diversify functions and tasks. And for example, fermentation of a complex substrates that require the use of several processes and metabolic pathways that is impossible to be carried by just one strain, but can be concluded using a co-culture, more than one microorganism. The second future for me in this field is the crossover fermentation. We can see a work in this paper. Crossover fermentation is a process in which a microorganism from a traditional fermentation can be introduced into a new substrate and or into a new compound in a new co-culture, and in this process can produce a new product. For example, in this paper, we can see the use of Aspergillus oryza from miso applied to a quark cheese process, traditional made from Lactococcus lactis. For me, the diversity of microorganisms from traditional process used in alternative substrates is a huge opportunity for the food fermentation industry on this moment worldwide, and this is a big opportunity for the industry because you can obtain a really quality different products using crossover fermentation. And the last one, the famous precision fermentation. Precision fermentation is when we use microorganisms genetically designed to produce bioidentical proteins. In this slide, you can see commercial products that use precision fermentation now in the market. The European Food Safety Authority, after this scientific colloquium, expressed in a note the understanding for this type of precision fermentation. And for EFSA, in fact, the question would be simple. We are talking here about the use of microorganisms and to produce these new products, regardless of whether they are produced with genetically modified microorganisms. If the final product contains recombinant DNA or viable cells from GMM, then the EFSA understands that it needs to be assessed as a GMO, a genetically modified organism. Otherwise, the EFSA understands that if no recombinant DNA or viable cells are present in the finished product, these new products in Europe need to be passed through assessment like a novel food. So, thank you for your attention. Here is my email and our location in the Brazilian map. We are here in an island, Santa Catarina Island, in the Federal University of Santa Catarina, in the city of Florianopolis. Just to finish, I want to show to you this for the Portuguese language audience. We produced it 1 year ago, this book called Microbiologia de Alimentos Fermentados, and I got a 30% discount for the audience if you want to buy this book. Thank you for the opportunity. Another time, Professor Todorov. Thank you. Questions? Let me see. Where can I see the chat? In the YouTube? No. The third one. Try the third one. No. I can't listen you, Slavi. Try?
Agora dá?
Okay. I listen you.
Okay, we're having a session for the questions. First, we can see the audience here on the red room at the Faculty of Pharmaceutical Sciences. Any questions from you?
You can ask in Portuguese, and we can translate.
Okay, I have a question. We're having a big problems in the last years with the gluten.
Yeah.
Do you have any experience to reduce the gluten in the food products by lactic acid bacteria, maybe application? Some work is done in Italy. They're using some specific starter culture that can reduce the gluten. But do you have any experience in this direction here in the Brazilian country? Country is like almost a continent, so.
Yeah.
Can you comment on this, maybe?
No, in our study, we try to better understand the situation here using our sourdough, and found some interesting things linked to the linked to the production of the acid, the production of the lactic acid during the sourdough process help this degradation of peptides linked to the celiac patient, linked to the intolerance of gluten. But we need to go ahead with this research to understand better which type of peptides can be degraded, and for sure test this situation in vivo in patients in a controlled way in vivo tests.
I think we have some questions from the audience, and Wellington will help on this point.
Test. So, can you hear me?
Yes. Good morning, Wellington.
Good morning, Juliano. Thank you.
Thank you.
From Carolina Curti. She wants to know if there is some criterion for selecting bacteria to be used in different food matrices, or is it just trial and error?
Yeah, a lot of published papers bring the protocol. We can find these tests to conduct in a organized way. A lot of tests to understand the safety of microbial culture. For sure, we need to the first tests need to be tests related to the safety of these strains, the production of antimicrobial compounds, the susceptibility of antimicrobials and antibiotics is the first phase of the research. After that, we will try to understand what do you need, what is the functionality that you need for your product, and enter in the late phase of technological tests to understand the power of your culture of isolated strain. But the first thing to do is test the safety of this strain.
There was a movie a few years ago of an airline company that was telling safety is priority. But I mean, in the microbiology, this is as well, it's a priority because we don't want to create a new Frankenstein, right?
Yeah, we need to create a Frankenstein, yeah.
To be sure that, I mean, if we think about the Hippocrates swear that the medical doctor do, they say first, we're not going to do nothing bad to the patient. So this is the same thing for the microbiology. We want to be sure that everything is safe, and then if we can help, this is excellent thing, but we don't want to do nothing wrong. More questions?
Yeah, I agree.
Well, depends if you want to give it to the mother-in-law. This is a different story, but
yeah. But if you need to think if the use will be for a food or for a biotechnological product.
Yeah,
the safety is not so important for a biotech product that will be a new molecule, but for a food, the safety is first.
This is what I agree that if we're going to do a production of the enzyme, we can even use the pathogenic strain because in the bioreactor we have controlled condition. But if you're going to release this in the food products or release in the nature as a probiotic or beneficial culture in the nature, we need to be sure that we are really having a safe strain that we can release and use in the process that we want to conduct. Any questions here from I think we have from the internet as well, Wellington?
Yeah, if no one has questions, I'm sorry if I mispronounced her name, Shaklo.
She's from Kazakhstan.
Okay. So may LAB be used for prevention of potato bread disease? Do you have any research in this field? It's very specific, I'm not sure.
Potato bread disease. Potato disease is like a phytopathogenic potato bread disease. Maybe are you talking about Bacillus subtilis rope spoilage in bread?
There's several microorganisms that are associated with the potato plant. So
potato plant, not potato bread. Okay. No, I don't know. Maybe this is a fungal pathogenesis, and the use of lactic bacteria can be studied. But I don't know.
Maybe this is a good idea for the future research and collaboration.
Yeah, to develop a PhD on this area.
There's more questions? Okay, if we don't have more questions, thank you very much, Luciano. It was a pleasure to have you in this direct contact from Florianopolis. Enjoy the good weather there. It's very cold here, most probably cold here as well. But thank you again, and hope to see you soon in some of the events that we have in Brazil or maybe outside. And it was really a pleasure to have you with us today. So we're going to have a few minutes of break now, and the next presentation will be direct contact with New Zealand at 11 o'clock. So for the people here in the audience, you can have a short walk for 5 minutes. For the people from online audience, will be some advertising videos. Thank you. Atrasado? Ah, não, é meu.
Pronto, 3 minutinhos só.
É atrasado? 5, 3, é diferente. Vamos ser da maneira latino-americana, tudo atrasado. Na América Latina, você pega isso, você fala para 2, 3 horas sem parar, né? Se você quer ir para a banheiro, agora é bom. Assim funciona.
Som.
Okay, now I need to repeat everything because the microphone was not working. So next presenter that we have today, it's Tony Mutukumira from University of Massey in New Zealand. Tony, it's originally from Zimbabwe, born in Zimbabwe, and then study his master and PhD in Norway. Then he moved to work as a professor at University of Massey in New Zealand. His all his experience is associated with the food microbiology, developing of the different food products, evaluating several traditional food products from New Zealand, including he's one of the pioneers working on kombucha and some of traditional bread products in New Zealand from the traditional tribes. Evaluating the interaction between different microorganisms in them, how they actually fermentation process work, why it's what's happened, how it's happened, and all these details. Unfortunately, because of the big time difference, 16 hours with New Zealand, presentation of Tony will be registered, and he will try just to lock in the end, maybe to have some of your questions. So please, we can have the presentation of Tony.
In the afternoon in Brazil, and it's very early morning in New Zealand. Welcome to this lecture and welcome to the winter seminar series on microbiology. Firstly, I would like to thank Professor Todorov for making this arrangement and for inviting me to participate in the winter seminars. Now, my topic is sour, salty, and alive, fermented foods and the evolution of starter cultures. My name is Tony Mutukumira, and my email is indicated there if you need to contact me. Now, let's look at how my lecture goes today. The outline of the lecture, I'll give a brief history of fermentation, and then I'll focus on the sour, salt, and alive products. Typically, I want to give you two examples which I've selected, which represent the sourness and saltness of products, fermented products. And then I'll talk briefly about the fermentation process, some characteristics, and some challenges, which will take us to the opportunities. Then I'll look at, if we were going to develop a starter culture, what are the first steps we need to do with respect to sauerkraut? And then the first steps as well, and a synopsis of pilot scale setup for kombucha. I'll give some acknowledgements, and more importantly, I have selected a few questions which I have placed in the last slide as a post-lecture discussion. Now, the history of fermentation. Indigenous fermented foods have a long history, and that is well documented since the human beings started to do what we call domestic agriculture. And fermented foods, they constitute an important diet in traditional communities. Traditional communities or indigenous communities, sometimes they are called. So you will find that the word traditional and indigenous being used interchangeably. These products, the demand for these products is increasing on the global market. And why are they increasing rapidly? Is because they are perceived to be healthy products. They've got healthy benefits, such as antioxidants, probiotics, which are live beneficial microorganisms. You cover that in the seminar series this week. And also they are known to have anti-inflammatory properties, detoxification, antimicrobial, and several other benefits. This is the reason why they are increasing in demand globally, this product. And this is really going to be the situation for the next few years, if not more, that the demand for fermented foods is going to continue. Typical products of traditional fermented foods or indigenous fermented foods, beer has been there for a long time. We believe, I don't know it according to literature, was one of the earliest discoveries in or documentation in traditional fermented products: bread, wine, yogurts, cheeses, tempeh made from fermented soya bean, sauerkraut, which I'm going to feature, and kombucha, which I'm going to talk a little bit more. Now, typical traditional fermented foods characterized by sourness and saltiness with live microorganisms. I've given, let me move my picture here. I've given an example of only 2 products, but there is a whole lot of products out there in traditional communities, indigenous communities, and also now in the commercial market, which are characterized by sourness and saltiness. We have got kombucha here, which is typically a sour product, and it contains, or it is fermented by acetic acid bacteria and yeast, and sometimes it is reported that it may contain some lactic acid bacteria in very small quantities. Then we have the salty product resembling the salty group is sauerkraut, which is fermented cabbage, typically fermented cabbage. It is fermented typically by LAB, lactic acid bacteria. Now, what is common between these 2 products, say the sourness, the sour product, and the salty product, they all contain live microorganisms, which are perceived or believed to be beneficial microorganisms. And the word perceived or believed, I am using it cautiously because a lot of these microorganisms, a lot of research has been done in vitro, but very few research or studies have been done in terms of in vivo, using animals or human beings to authenticate the probiotic potential of these products. But it is believed that you and me, if we consume these products, they are actually beneficial to our health. They complement the probiotics. It is believed they complement the probiotics in our gut, gastrointestinal tracts. Now let's move on. Let's look at the characteristics of the fermentation process. It's a bioprocess using microorganisms and their enzymes. And in the previous slide, I indicated to you, with respect to kombucha, it's fermented by acetic acid bacteria, and sauerkraut is dominated by lactic acid bacteria. And of course, their enzymes are the ones which are carrying out the bioprocess of fermentation. Typically, these enzymes, these microorganisms, or the enzymes from these microorganisms, they metabolize the sugars during fermentation to produce what we call volatile and non-volatile compounds. Typical example of the non-volatile compounds which really dominate, characterize these products, is the organic acids. And the organic acids, it's a range of them. In kombucha, the dominant or the acid which has got the highest concentration, which is present in the highest concentration, is acetic acid. And in sauerkraut, it is lactic acid from metabolized from or produced from lactic acid bacteria. And these organic acids are the ones which suppress the pH to lower levels, making the product a little bit more favorable for other microorganisms to grow, but more importantly, making the product safe to consume. And also, they can be stored for a longer period. The fermentation also produces unique flavor compounds in the two products. I will not go into that today. Also, another aspect, they also produce antimicrobial compounds. I think this will be covered substantially during the seminar. And it is also documented that they metabolize proteins and other compounds to produce a range of flavor compounds and antimicrobial compounds, which are desirable for the products. That gives the product a wholesome state, which is both nutritious, which is safe, and can be stored for a longer period. The fermentation technology, what are the challenges? So what I have covered in the last few slides is to give you just a synopsis of the products which are produced during traditional fermentation or indigenous fermentation, which have been going on since the human being started domestication of agriculture, which means organized agriculture. It has been going on as far as that period. Now, this fermentation, it is produced, it passed on from one generation to the other. In most cases, no documentation except that people just narrate the fermentation process and they pass it on to generations down the stream. This constitutes a lot of challenges. The main challenges are because we are relying on spontaneous natural fermentation. Essentially, we prepare the products, put them in a suitable container, and we leave it to nature to initiate fermentation. So it is spontaneous, it is natural, it is not controlled. So it relies on, if I may use the term, Mother Nature. The fermentation is initiated by inherent or environmental microorganisms. What do I mean by that? The microorganisms from the environment, because the environment is not sterile, and also the microorganisms which are on the surfaces of the products. On the surfaces of the products, microorganisms can harbor there during harvesting or during preparation, and they can initiate the fermentation, those microorganisms, which means if the process is uncontrolled and it is triggered by what you call spontaneous fermentation, the product quality is not consistent and the product quality is not predictable. You cannot state that the product which you produce today will be the same as you produce next week or the week after, or even tomorrow. It is variable because of a lot of factors which are also variable. They are not stable where these fermentation processes take place. So this can result in persistent failure of fermentation processes. For example, typically in winter, temperatures are a bit lower. Probably not in Brazil, but other parts of the world, like in New Zealand. Today, for example, temperatures were below 10. So if you are carrying out natural fermentation induced by spontaneous microorganisms, well, your process will take place, but will be very slow. That means it may even fail, which means you may not promote the desirable microorganisms to be dominant, which are required for you to produce the product of the desired quality. So in Brazil, probably temperatures are quite consistent, but you are fortunate to be in that part of the world. Now, since time immemorial, people have said, okay, natural fermentation, spontaneous fermentation is unstable. So they also use another technique which is called backsloping. This is to assure yourself that you can get a product which is similar or consistent, of a consistent quality. And how do they do that? By backsloping. They use the previous batch. And in most cases, they use the same containers. These containers have got some pores. And those pore microorganisms harbor or they colonize the pores, which means when we introduce a new product, those microorganisms will be available and they will act like a starter culture. They will initiate fermentation, which means your previous batch and your next batch, if you use backsloping, is likely to be, well, more or less the same. Now, the microbial composition of the starter cultures is diverse and largely undefined. That is, in general, whether it is backsloping, whether it is you're relying on spontaneous natural fermentation. But when you use backsloping, it is interesting. When you use backsloping, well, if you use that for a long period successfully, you are going to create more or less a defined sort of a culture without unknown. The composition is not known, but the culture may generally be the same from day to day by using backsloping. But that does not translate into you producing a good product, because you really don't know your microbial composition of the starter culture in terms of at strain level or species level. Now, how can the fermentation be improved? So these are a few challenges, and these challenges are the ones which have triggered us to move on to thinking about we need cultures with predictable fermentation characteristics, with predictable fermentation behavior when we introduce them into our desired materials to be fermented. Now, traditional fermentation technologies gives us these opportunities. Having looked at the challenges before, it gives us these opportunities. What are the opportunities? We can produce consistent high quality products if we develop a starter culture. We can increase the scale of production. That is also an opportunity by actually developing starter cultures, producing a consistent high quality product and increasing the scale production from small scale production through to large scale industrial fermenters. It also gives us an opportunity to align production with local food laws. Previously, what I've covered, those products are being produced in households, rural areas, sometimes in urban areas around the world. Very few of them follow any, if I may just be a little bit liberal, no food laws, no food regulations. So if they are spoiled or they are contaminated by pathogens in somebody, it leads to people getting ill, foodborne illness. Well, this is the reason why it can do that, because people are not following food laws, which essentially are developed at the national level to produce products which are safe for human consumption. Now, the opportunity we have of using starter cultures, we can reduce the rate of production failures. We can also prevent spoilage caused by pathogens, which I have indicated there. So using characterized cultures with predictable performance is attractive. And we can also create commercial business, by developing cultures with predictable characteristics. Now, I want to look at our first product, how we can initiate, what are the first steps for producing a starter culture. As I mentioned at the beginning, sauerkraut is produced or is made from traditionally from white cabbage, which, well, it's not quite white, but this variety of cabbage, but a number of varieties of cabbages can be used now. We can have red cabbage, we can mix red and white, we can have all sorts of cabbages which are produced around the world to produce sauerkraut. This is shredded, sprinkled with a certain amount of salt. Now, the amount of salt you use there depends on the traditional practices. Some people may use as much as 20% salt. Of course, we would like consumers nowadays to be a bit more moderate in terms of consuming sodium. So people can go down to as much as 1% salt. However, the choice of salt, the level, depends on the practice or the tradition or the microorganisms which probably are harboring or are initiating the fermentation. Because remember, we don't have a starter culture at all. We are going to initiate natural fermentation here. So we are starting to prepare our sauerkraut. So we shred this. Now, the sizes can be as small as 2 millimeters shredding. We pack them accordingly into suitable containers. We really squeeze hard, press them hard into those jars. Typically, people use glass jars. After you sprinkled with your salt, let's say it ranges from 1% to 20% salt. Some people also add some condiments, like caraway seeds, for example, to add. They claim to add a bit of flavor. But for me, I often question, right? If we add caraway seeds and all those condiments, are they playing a part in the fermentation? Actually, that question has not been answered at all. So far, I haven't seen any published data which talks about when they add the condiments, caraway seeds, and any other flavors, do they impact on the fermentation? That we don't know. But that is added, and we allow natural fermentation to take place. Natural fermentation can take place at room temperature. But you know, when you say room temperature or ambient temperature, it depends where you are. Allow me to say you would want a temperature of around 20 degrees, 18 to 20 degrees Celsius. And that fermentation can go on up to 7 weeks, 6 to 7 weeks. Also, that it depends on the type of microorganism and the practice which you would have, which you have accustomed to producing a good sauerkraut. Nonetheless, you allow the natural fermentation to take place at desirable optimum temperatures, if I may use those statements. And you come up with then you have your finished fermented sauerkraut here. Now, we are interested in the finished product, not for consumption, but to isolate our microorganisms, right? So what we do, then we have got our fermenting cultures in here, and we have added our salt, which selects desirable cultures. Now, salt plays a very important part. One is to flavor the product, but two, more importantly, it will suppress all those microorganisms which are not salt tolerant and allow the salt tolerant LAB to flourish or to dominate. And that is really the backbone of sauerkraut fermentation. Okay. Now, once we have got our cultures here, now we can go to the next step. Okay, my slide is a little bit not moving here. Let me juggle it a little bit. Now we go to the next step. This is really a summary of what is taking place. There are many ways of isolating your cultures from your sauerkraut, but this is also one way. Now, when we have, let me go back a little bit, right? When we have our fermenting cultures, right, in the sauerkraut here, right? So our idea is we would like now to isolate. We want to harvest these cultures here. Remember, these cultures, they are just wild because they came from a wild environment which colonized or which were dominant on the surfaces of the products, and now they've done the job. They've been selected by the environmental conditions in the fermentation process. Now we've got our cultures here. Okay. Now, what do? In terms of sauerkraut, we take the juice, which is the sauerkraut juice, which is very salty, the brine solution. When we add salt, as you know, into water, we can call it salted water, but we can also call it brine water. So we take that brine water and we go through a series of dilutions, typically 10 times dilution to 10 to the 7 dilution. So we aim to go as low as possible and as high as possible, because ideally we do not want to miss any, because at the moment we don't know which dilution is likely to, where we are likely to capture our desired microorganisms. One important point I should have mentioned is that during fermentation of sauerkraut, right, when we are fermenting allowing our sauerkraut to ferment from week 1 or from day 1 or week 1 to week 7, we would like to sample as frequently as possible. Now, for 7 weeks, it's practically impossible to do it every day. One is very costly, and it is also cumbersome. So with sauerkraut, it's very convenient, although probably one may argue that we can miss some important information, but it's very practical to sample every week, so we can end up with 7 samples from one batch, for example. Now, if the resources permit, you can take 2 sample. You can sample every 4 days until 7 weeks or 6 weeks, or until you've fully fermented your sauerkraut. You culture using the medium, which is favorable for growth of lactic acid bacteria, which is MRS agar. You incubate anaerobically because we want to promote the growth of LAB at 37 degrees, for example, for 72 hours. We carry out some enumeration. We do some colon selection and purification. And when we have collected our desired isolates here, we can store them in 70% saline glycerol solution, and we can store it minus 80 degrees Celsius. Now, what I have here is really what you have done in the labs many, many times, where you've done serial dilution, and you go through a series of plating using surface plating to purify. So this is just showing you or reminding you some of the, what we call, the classical techniques which you have to go through. Now, once we have done that, we can subject our cultures to genetic sequencing using different probes or primers which are available. Now, also, if funding permits, you can also, instead of going through the series of plating, which I have indicated before, you can come actually directly into genetic sequencing if you can harvest your DNA from the LAB, and you can carry out a number of steps using established genetic sequencing system as shown on the slide here. I will not go into the details of this because you are going to cover this later in the seminar. So that way you would have now, this allows you to identify the microorganisms, which we can call dominant microorganisms, which are fermenting, and we believe they are lactic acid bacteria. So you've identified, you know what they are at species level, you know what they are with strain number after genetic sequencing and after you carried out a number of techniques during this particular session of genetic sequencing. So you know what you have. So what you can do now, you can preserve your cultures in appropriate media, and you can store them for, we can have what we call short-term storage, and we can have what we call long-term storage. In long-term storage, we normally use the minus 80 degrees Celsius freezer, and short-term, we can prepare them in a proper way, in an appropriate way, and you can store them in the refrigerator, which you can be maybe using them every 2 days or a few weeks or so. That's what you do. But your bank, you keep it under minus 80. You want to keep it for a very long time. You can keep it for a lifetime if you preserve that very well. Now, I want to turn my attention to kombucha. Right. What are the first steps to developing a potential culture from kombucha? Now, what I've done here, I've put everything in one slide. The reason is kombucha is a little bit demanding. It's not as straightforward as dealing with sauerkraut. Now, we start in the same way. We have to prepare our product in a traditional manner. Now, actually having to say prepare, I would like to say it is also what I did in myself in my own PhD is actually to go and collect samples from the traditional producers or the indigenous producers at household level. You collect the samples, the actual finished samples. In fact, I used to stay there and observe the entire process. So you can take samples at the beginning and as frequently as you can until the last sample, and you can keep them in the chilled conditions and transfer them into the laboratory. So you can actually collect them in the indigenous communities. Or you can prepare these products in the lab by yourself. In terms of sauerkraut, you can work with the indigenous quite easily. With kombucha, you can, but it is quite a demanding product because it does require some skills, which perhaps the people in the indigenous, they don't observe periodically what is taking place. But nonetheless, I can give you an overview of what is taking place here. Typically, kombucha is prepared from black tea and some what we call organic whole sugar. Yes, I've written, you see here white sugar, but this is actually organic sugar. This is what you would like to use, and some black tea. I'm not promoting Bale Company, and I'm not promoting this company either. It's unfortunate. I just wanted to show these pictures. You prepare this in appropriate proportions. You can ask, what are the appropriate proportions? It really depends, but I can indicate to you that normally some people they use 5% sugar, 5% tea, and they can use about 10 to 20% sugar. In that we are talking about, and then you dissolve or you mix this in water, in boiled water, and then you have your sugared tea here, and you allow that sugared tea to cool down, and you add your culture is composed of two components. One is the broth from the previous batch of kombucha. Now, remember, we are preparing this in the indigenous way or traditional way. You have your broth, and then you also take a bit of the cellulose. Kombucha is exciting to work with. You've got the cellulose part, which develops during fermentation. So you need to slice a bit of that and then the broth. Why do we need to take the cellulose? Well, it's very interesting because the microorganisms in the broth and the microorganisms in the cellulose may not be the same. There are some which may favor to grow in the cellulose or promote the growth of cellulose. What are those? Those are the microorganisms which have got affinity for oxygen. So it's important that you take some microorganisms from the cellulose and some microorganisms from the broth. You sample those, and that is what you call your culture. And then you add it when this is cold. Then you allow it to ferment, and you have to cover this with a cover which allows air to go through, because oxygen is very important for these microorganisms. Unlike the sauerkraut, they prefer an anaerobic environment or microaerophilic environment. Now, once you have done this, you take your representative samples. Like I said here before, you can take your samples every 48 hours, or you can take it every 24 hours, depending on your resources. You prepare dilutions, and then you go through all the isolations which are required, which is just traditional microbiology, and you examine, and then you screen the isolates which you get from here. You screen. Why are we screening? We need to screen and take those ones which we think, based on the knowledge we get from the published domain, which are likely to be responsible for the fermentation of kombucha. So in this case here, our target is acetic acid bacteria and yeast. Now, once you have screened here, and you're examining here using different techniques, once you have screened and you've taken some samples and you extracted the DNA, and then you go through genetic sequencing. For yeast, you use the 16S sequencing, and for the AAB, we use the 16S, and for the yeast, we use ITS, internal transcribed spacer technique, and you do DNA sequencing. Now, once you have identified your microorganisms, which we expect to find AAB, and we expect to find yeast strains in kombucha. That's what we expect. And then let's look at typical examples. Now, the challenge you have, you can see here. Let's start. I should have probably mentioned this a little bit earlier, but nevertheless, typical examples of LAB isolates found in sauerkraut are these ones here, which I should have given you a bit earlier, but I wanted to just give the whole lot. Now, there is an interesting microorganism which is called Leuconostoc mesandroids. It is believed, and it is true, that it actually also part of the fermenting microorganisms in sauerkraut. Now, Leuconostoc is a very demanding type of microbe. Why is it demanding? It is demanding in terms of its nutritional requirements to grow. So it doesn't grow that quickly and that easily. It is believed that it dominates at the beginning of the fermentation of sauerkraut. Apparently, it dominates at the beginning before the other microorganisms here, the fermenting microorganisms, take over. But I would like to say that in our work, we did not find any Leuconostoc. So I put a question mark there. Sometimes you find it, sometimes you don't find it. But what is required is that it is important to consider that Leuconostoc mesandroid species are part of the fermenting cultures in sauerkraut. Now, let's turn our attention to the kombucha cultures. We have got a group of isolates which belong to the acetic acid bacteria. Typically, you've got the mast, you've got the rotidus, and you've got potas. This one which I've marked here, apparently that particular species is responsible for forming the cellulose, which is the one which floats at the top of the liquid while you're fermenting. So it is important that when you are sampling, you also take samples from the cellulose, because you may miss some of the species. Now, I'm also pleased to say to you that my PhD student, Boying Wang, who is defending her thesis next week, she actually she reported, and this is the work is published, she found some of these strains in kombucha. So I've marked here, Saccharomyces cerevisiae is one of the dominant yeast, by the way, sorry, this is a group of yeasts. Some of the dominant yeasts which are responsible for fermenting sugar or metabolizing sugar in kombucha. Once that drops the pH, and then the acetic bacteria come in, and there is a whole lot of metabolic activities which take place in kombucha. It's quite exciting. So this is the situation you have. Now, with all this, it means that if you are going to make your own, you are developing a starter culture, the question is, do we include all these microorganisms in terms of kombucha? And in what ratios? And it's very, very challenging. Now, the same way goes here as well. If we are going to develop a sauerkraut culture, standard culture, do we include all this? And also, even if we did not find any Lucno stock in our search, in our particular samples, should Lucno stock be part of this or not? Or should we select a few or not? Now, developing a starter culture, one is exciting science. Two is very expensive and very demanding. As I indicated, this is a PhD student, took 4 years to get to this point of being able to achieve this. However, it is exciting in terms of a good science, but you need the resources, financial resources, and also the infrastructure. Now, I will move on. All right. When we have our cultures, it is important. I'm giving just this an example. This is an example of kombucha, in fact. We need to characterize using various techniques. What does it mean, characterization? We need to know what are the different characteristics of these microorganisms. What do they do in terms of gram reaction? Are they positive, negative? What do they do to the oxidase, the catalase? Ability to form cellulose. I'm giving you an example of kombucha. You can see here, very interesting, in fact, if I may talk about kombucha, you can see here, those which belong to group 1 and group 2, they didn't form any, couldn't form cellulose, but from group 3 to group 6 formed cellulose. That's interesting for our kombucha. And we also look at their ability to metabolize ethanol, because kombucha, typically, nowadays people produce what they call hard kombucha, because, people like to enjoy a bit of alcoholic beverage. But typically, when it is developed at the household level in indigenous communities or traditional communities, this is a non-alcoholic beverage, should be consumed by young people. But people nowadays are producing hard kombucha in various communities. That's a different story altogether. So look at this. We have to characterize, and so that we get to know, generate a bit more information about our cultures, which we've isolated. Now, this is typically characterizing kombucha. And I could have another set or another slide showing characterization of lactic acid bacteria, showing some of the characteristics which are interested in sauerkraut. Now, I will move on. Right. I said I'm going to give you a bit of the side of the kombucha, and which resembles the same pathway of characterization. Now, at the beginning, I emphasized a lot about these products, kombucha and sauerkraut. One of the main drivers in terms of being produced at indigenous level, and also now that they are being scaled up, is because they are considered to be beneficial. Essentially, we are looking at the antioxidants, the vitamin C, for example, in the two products. For example, we can say antioxidants, we can get that in tea. We can also get antioxidants in cabbage, although that may be a bit low, but vitamin C is certainly attractive in cabbage. And of course, the cultures themselves, people claim they are good bacteria. They are probiotic, which means if you consume, they can confer good properties in your GIT, gastrointestinal tract. Now, this slide here is meant to emphasize that before we can talk about their potential as probiotics, we need to check some properties which are as shown here. We need to check their stress tolerance in the environment. You remember, now these products will be consumed by you and by me as well. We need to check their stress tolerance when we consume them. Remember, in our gut, we have got high acid, very low pH, high acid, pH of believed to between 2 and 3, if not lower. We need to check that. Cell surface characteristics. How does it behave at the cellular level? And the functional properties. And more importantly, are they safe? These cultures, are they safe? So we need to carry out a number of tests before we can claim that they are probiotic. Remember, when our old folk consume this product, they have a strong belief that these products are beneficial. And we don't want to question that. All we want to do now, we would like to document this with good science and share with them at the rural level or indigenous level. Now, yes, I've moved on to this one. Now, another aspect we need to do with respect to kombucha now, we need to do what we call, sorry about that. We need to do prototyping. Now, this slide is to prototype, to make our kombucha. Now, when you're prototyping our kombucha, you need to use very high-level factorial designs. The reason is you've got a lot of factors. Let's start on this side here, on the right side. You need to select suitable sugar levels. You cannot continue to say, oh, I use 20% and that is suitable. That environment was not controlled. Now we are trying to test our cultures selected from the pool, which I showed you before. And we can now test it at different sugar levels. Why would you want to test different sugar levels? Is because today, the consumers who are demanding these products, they are saying we should consume low sugar levels. So we want minimum sugar, minimum quantities of sugar, which can produce a good kombucha. We also want minimum, probably don't want to have too much tea in the kombucha. Why don't you want too much tea? Too much tea can also, black tea, it depends which one you are using, different teas, can actually be very harsh. And we don't know whether it will be able to promote, at what level that type of tea will be able to promote the growth of the culture, which we are putting together, prototyping. Now, here is a difficult section, your inoculum. You've got all those cultures which are purified. You saw a whole lot of them. Do you combine them in that large batch or you select a few? I leave that to you to think about now. And remember, when our inoculum here has to have bacteria and yeast. And at the same time, remember, at the same time, when you're saying we need bacteria and yeast, we need to have an inoculum which is contains a certain proportion of this. because they operate in a symbiotic, they grow in a symbiotic nature, beneficial to one another. And normally we call this a SCOBY, symbiotic culture of bacteria and yeast. And that means we need both the bacteria, the AAB, and the yeast together, giving us our SCOBY. Now, we turn on to this. This is some of the factors. We continue with the other factors. Temperature. Temperature in indigenous communities at traditional level fluctuates. And I would like to share with you that even the industrialists who are trying to make this product, they have got quite a challenge. Because in the factory, some of the factories, temperatures fluctuate. I'll tell you what, I visited one small scale trying to produce this product here. And the producer told me that the temperatures around in one area, in one room, fermenting area, every corner is different. That was quite interesting. Then the time of fermentation, then the tea infusion time. How long do you infuse the tea? That's the reason I talked about the concentration here. It also has to go with the time of infusion. So you need now to factor in the fermentation conditions on the left side here and the formulations on the right side here during prototyping. Now, and this gives you, when you get this product here, you characterize that product both using microbiological techniques, physical techniques, measuring color, for example, and you also can carry out some sensory evaluation to find out how well your selected formulation is worked out. I can indicate to you that you would have to go through many, many formulations to be able to come up with something which you can call good kombucha. Because good kombucha is prepared by some old folk down in the rural villages where they prepare things by instinct. They don't read. They can read, but they don't have a formulation to take from. But all they do is they say, take 1 spoon of that, take 2 grams of that, take 1. In fact, if they take 2 grams of that, they're even being, that's even higher up. They are talking about take a scoop, a spoon of that, scoop a bit of that, scoop a bit of that, and mix together. And leave it for some time. How long? Oh, leave it for some time. So that's what you get in our indigenous communities, which is very exciting. And I do miss that. Anyway, I have to move on to the next one. Now, what I'd like to do here, I've come to the end of my presentation. I sincerely want to thank wholeheartedly to Professor Todorov for organizing such a wonderful winter seminar. I have learned a lot of what can be done. It's a shame that I cannot join you during the normal seminar time because of the time differences. And because it is exciting, I would be able to meet international people. But I also want to thank him for also giving me the opportunity to participate in the winter seminar and to interact with the students. I hope I'm interacting with you in one way or another, although I'm not able to see you, to interact with the staff at the University of Sao Paulo, and also to interact with international scientists from elsewhere around the world. So thank you very much. But before I go, I would like to give you something to chew. As we always recommend in academia, it's always good something to reflect. So I prepared a post-lecture discussion for you with 6, sort of questions, so to speak. You can discuss this in groups, or you can discuss this post-lecture as a discussion in the seminar room in the entire seminar, in the lecture room. It depends what Professor Todorov would like to do, how to deliver this. I prepared quite a bit so that you can break it up and have brainstorm. And more importantly, I really want you to find out not about kombucha and sauerkraut, other traditional fermented products produced in Brazil. Are they commercialized today? Are they produced at large scale, fermenters or not? I know you are going to talk. You may mention beer. That's fine. There are different types of beers. It would be good to know. I will not be able to know this myself, but one day I'll probably be able to share the information, or Professor Todorov will be able to share information with me at a later stage. But more importantly is for you to maybe to give you a bit of my story from New Zealand. With that, I wish you a very successful and entertaining winter seminar series. I say goodbye for now.
Thank you very much, Tony, for the presentation. Most probably you're sleeping now. We're going to have a lunch. We're going to have a questions later from 3 to 4. It's a discussion session. 3:15 to 4 o'clock. So if you have your question, we can record them and we can try to see if Tony will be available in the discussion section, because it's more reasonable time for him later. Brazilian time from 16-hour difference is just the morning. Well, now we're going to have a break for lunch, 1 hour, and we'll be coming back in 1 hour from 1 p.m. Brazilian time. That will be 6 p.m. Central European time, so you can calculate your time zone. So thank you very much for the participation in the first part, and see you in about 1 hour. Boa tarde. Good evening, good afternoon, not evening. Well, good evening for people in Asia. Good morning for people from Hawaii. And good afternoon for people from North and Latin America, North and South America. This time, I think the microphone is working because in the previous time was not put the microphone, so was needed to repeat. Next presenter, it's from Brazil, from University of Unesp, São José do Rio Preto. It's Ana Lucia Barreto Pena. She is a professor in food technology with a very good, interesting focus on dairy products. And if you have questions about the cheeses, you can always ask Ana Lucia because she worked, I'm not going to tell how many years because I don't want to reveal her age, but have a good experience in the work with the cheeses. At the moment, she is in Switzerland doing some tasting of the cheeses, not working, just enjoying the cheeses. So we're having her presentation as a registered video, and you can have her presentation. She promised that she would try to lock in the system for the question session in the end of the today presentations. She have her master and PhD from Sao Paulo University, USP, and since she started her work, she's in campus of Unesp in São José do Rio Preto. As I mentioned, several projects on the cheese, microbiota of the cheese, beneficial properties, animal models, so it was quite a wild selection of topics.
Fermented dairy products. Good afternoon. I would like to thank Professor about fermented dairy products, rediscovery and innovations. I am Ana Lucia Barreto Pena from São Paulo State University. Today, my talk will be divided in two parts. The first about the historical overview of fermented dairy products, a topic about fermentation process, including the characteristics of the microorganisms used in dairy fermentation, probiotics, and their health benefits. In the second part, a summary of the production technology in traditional fermented dairy products, some innovation in fermented dairy products, and future prospects and research directions. The historical overview about fermentation, it is considered a metabolic process that converts carbohydrates to acid gases, alcohol, or flavor compounds using microorganisms like bacteria, yeasts, molds, and fermentation is affected by many factors, such as temperature, pH value, oxygen availability, and time. It is used as a preservation method for enhancement of nutritional value and development of unique flavors and textures. There are archaeological evidences of fermentation milk products in Mesopotamia since approximately 5,000 years before Christ. Fermentation dairy products have cultural significance across many regions. In Europe, cheese-making traditions date back to the ancient Greek and Rome, and an expansion of cheese occurred to their domains. In Middle Age, the development of various cheese in monasteries, such as Port Salut, Münster, and Mahual. In Middle East and Central Asia, there are historical texts and recordings mentioning the development of fermented dairy like yogurt and kefir. In Asia, other types of fermented milk were developed, such as lassi, dahi, and yak. The Pasteur's discovery in the 19th century revealed that the presence of microorganisms in fermentation determined the types of products. It was also then when the isolation and selection of microorganisms took place. Milk pasteurization was also a landmark in food preservation. It was also possible to produce safer dairy products during all year. And the industrialization favored the fast dissemination of dairy products. Since then, many products of dairy products have been produced all over the world. Bacteria, yeast, and molds are used in dairy fermentation. Lactic acid bacteria, also called lab, are used as a starter culture for fermentation to produce acid and flavor. They can be mesophilic or thermophilic, depending on the temperature of growth. Non-starter cultures are important for producing aromatic compounds and texture compounds, such as exopolysaccharides. In some types of products, a secondary fermentation is applied to promote surface cheese ripening which contributes to flavor, texture, and appearance. Propionibacterium and Brevibacterium linens are used for this purpose. Molds such as Penicillium camembert and Penicillium candidum are used to give ripened cheese a particular surface or veins. In fermented milk, yeasts are used to promote alcoholic fermentation, development of flavor, and carbonation in kefir and kilns. Saccharomyces and Cleveromyces species are used for this purpose. The fermentation pathway can be described by the main metabolites produced during fermentation, according to the microorganisms used. Lactic acid fermentation is essential for dairy products to produce of acids and flavor compounds. The propionic acid fermentation is responsible for the production of flavor compounds and ice formation in Swiss type cheese, while the citric acid fermentation results in production of light flavor compounds for many products like butter, fermented cream, cottage, and other cheese. In contrast, yeasts are responsible for the conversion of carbohydrates into alcohol in some dairy products, such as hummus and kefir. The production of butyric acid, on the other hand, gives cheese an undesirable flavor. Lactic acid bacteria are present in many types of foods, such as cheese, yogurt, fermented milk, chucrut, pickles, fermented meat, olive oils, wine, fermented dough. They are also present in the microbiota of mouth, intestines, skin, and vagina of mammalians. Many lab species are also associated to wide health benefits, mainly related to the gastrointestinal tract of both humans and mammalians. Lactic acid bacteria have many abilities, such as carbohydrates, assimilation, and production of many metabolites, like organic acid, such as lactic, acetic, formic, propionic, and pyruvic, and volatile compounds, like diacetyl and acetoin. Lab can also produce many kinds of enzymes, such as proteases, peptidases, lipases, beta-galactosidase, esterases, exopolysaccharide synthesis, and aldolases, which are important to degrade the food matrix components. Some lactic acid bacteria produce antimicrobial substances, such as organic acids, oxygen peroxide, enzymes, and bacteriocins, and improve the safety of dairy products. In addition, specific lactic acid bacteria can degrade the food matrix and produce bioactive compounds, such as peptides, fatty acids, and vitamins, folate, cobalamin, menaquinone, vitamin K2, riboflavin, and thiamine. The use of lab to produce vitamins is a very interesting option to increase the nutritional value of products in countries with nutritional needs. Besides all these abilities, lab need to present industrial performance, which means functionality under food process conditions, such as fast growth, high biomass yield, high viability, and desirable technological characteristics. The strain that performs well with all these parameters have the robustness to be selected and applied in fermented process for industrial optimization. These lab strains can be applied in the production of fermented food and supplements, such as dairy products like yogurt, kefir, cheese, butter, meat products like sausage, curried meat, and also vegetables like pickles, chucrut, and beverages like wine and beer. In this table, we have examples of lab application in dairy products. For instance, Lactococcus lactis subspecies lactis is responsible for lactic acid, diacetyl, low gas, and bacteriocins production, and proteolysis in cream, butter, veal, buttermilk, and cheese. In contrast, Brevibacterium linens has the purpose to produce surface color and coating, proteolysis, lipolysis, and flavor in smear, soft to semi-hard cheese. What are probiotics? Some microorganisms are characterized as probiotics, which are live microorganisms that, when administered in adequate amounts, confer health benefits on the host. Specific strains of genera Lactobacillus, Streptococcus, Bifidobacterium, Saccharomyces boulardii, and Escherichia coli are considered safe and generally characterized as probiotics. However, the evidence of health benefits needs to be demonstrated to obtain the health claims of functional food. Here we have the timeline of probiotics. We can highlight some episodes. In 1878, labs were isolated by Lister. In 1879 and 1900, bifidobacteria and Bacillus acidophilus were described by Tisser and Moro. In 1930, Shirota commercialized milk fermented by Lactobacillus casei. In 1965, the first concept of probiotics was established by Lilly and Stilwell. More recently, in 2001, Fauhu defined probiotics, and in 2016, the guidelines for life biotherapeutics was established. The probiotic effects are classified as widespread among probiotics, such as colonization resistance, regulation of intestinal transit, and competitive exclusion of pathogens. Some of the beneficial effects are frequent and the effects are species-specific, such as gut barrier reinforcement, bile salt metabolism, and neutralization of carcinogens. However, some health benefits are rare and strain-specific, such as neurological and immunological effects. In this slide, we can see the mechanism of action, like competitive exclusion in the gut, production of antimicrobial substances such as short-chain fatty acids, bacteriocins, and hydrogen peroxide, enhancement of epithelial barrier functions due to the presence of mucous layers, defensins, and reinforcement of tight junctions, immunomodulation, and systemic signaling via nervous system to the brain. production of serotonin, dopamine, and gamma-aminobutyric acids. It's noteworthy that neurological, immunological, and the endocrinological are production of specific bioactive compounds are strain specific. What's the meaning of strain specific? Let me show you with this example. Here we have three well-known Brazilians. Gisele Bündchen, a Brazilian top model, Ayrton Senna, a Brazilian Formula 1 pilot, and Pelé, a Brazilian soccer player. All of them are from the same genus and species, Homo sapiens. However, they have specific abilities to be a top model, a great pilot, or a skilled player. They are unique as some strains of microorganisms, such as Lactobacillus rhamnosus, Bifidobacterium animalis BB12, and Lactobacillus caseae shirota. So, the probiotic effects demonstrated for one strain cannot be extrapolated to another strain, even if they belong to the same species. Intensive studies in this area have found new promising intestinal bacteria as new generation of probiotics, such as Bacteroides, Roseburia, Kermansia, Propionibacterium, and Fecalium bacterium. However, they also need to be evaluated for efficacy, safety, and technological aspect for a large-scale production. Additionally, they have some limitations because they are nutritionally fastidious and very sensitive to oxygen. Now, here is some information on traditional fermented dairy products, starting by the characteristics of milk and how milk components are affected by the treatment used in fermentation process, as well as some characteristics of cheese, yogurt, kefir, and fermented cream. It is important to remember the milk composition, which contains lactose, the typical disaccharide from milk, lipids composed by triacylglycerols, complex lipids, and unsaponified components, proteins, casein and whey proteins, minerals like phosphates, citrates, chlorides, sulfates, carbonates, and bicarbonate of sodium, potassium, calcium, magnesium, and vitamins. The operations used during the production of dairy products like fermented milk affect some components like protein. In milk, the main protein is casein, whose fractions are assembled in micelles, as represented here. When milk is heated during pasteurization or at higher temperatures, the whey proteins is denatured and linked to the casein micelles, as shown here. This affects the structure and composition of the product. In this slide, we can see the different effects on casein using rennet for cheese curd coagulation or acidification. In the enzymatic coagulation, the enzyme rennet acts by breaking the bond between the amino acids 105 and 106 of kappa casein, which is in the border of the micelles, and releasing the casein macropeptides. During the fermentation process, lactose is transformed into organic acids. The pH decreases and favor the casein demineralization, as we can see here, in which the calcium phosphate is removed from the micelles, resulting in a contraction of casein micelles and formation of the curd. Cheese is one of the main dairy products. It was first described around 60,000 years before Christ in Mesopotamia, near the Tigris and Euphrates River. The Greeks were the first Europeans to know cheese, which was considered a gift from the gods. During the Roman Empire, wars and invasions in different regions helped spread cheese to other continents. In the 19th century, after the introduction of milk pasteurization, cheese production was quickly disseminated to the world. Today, cheese are produced in many countries using artisanal and industrial methods. Basically, cheese production includes milk reception and selection, milk cooling and storage, preheating for fat and solids non-fat standardization, followed by pasteurization. Cultures for fermentation, calcium chloride, colorants, and enzymes are added according to the cheese. Enzymatic coagulation or acidification is obtained, followed by cutting and curd treatment. The curds go down and whey is drained and pressed. Salting can be carried out using brine or by addition of salt on the cheese surface. Afterward, cheese is ripened according to the cheese type. We can see the many variations of cheese processing to obtain different types of cheese. For instance, as mentioned before, the coagulation can be obtained by lactic acidification or using rennet. The length of draining, curd treatment, and pressing can result in many cheese varieties. The ripening time and type of microorganisms present during ripening also contribute to develop specific characteristics. Yogurt is a very old dairy fermented product. It dates back to the ancient Mesopotamia, around 5,000 years before Christ, a region of the rivers Tigris and Euphrates between the Mediterranean Sea and the Persian Gulf. It is traditionally made in the Middle East and Central Asia. For the fermentation process, Lactobacillus delbrueckii subspecies bulgaricus and Streptococcus thermophilus are used. Yogurt processing involves milk reception and quality evaluation, clarification, fat, and solids non-fat standardization. Depending on the type, addition of stabilizers, emulsifiers, and sugar, followed by homogenization and heat treatment. Cooling and addition of cultures and incubation is realized until the pH reaches 4.6. Afterwards, breaking the curd and cooling, followed by the addition of fruit pulps, colorants, and aroma according to the product. Finally, the packaging and final cooled are carried out. There are different types of yogurts. Set yogurts receive the pre-treatment, the cultures are added, and they are packed. The product ferments in incubation rooms followed by cooling. In contrast, starred yogurt ferments in tanks and then cooled and packaged. Drinking yogurt is also fermented in tanks, cooled and homogenized before packaging, while a concentrated yogurt after fermentation is centrifuged to partially eliminate the whey and it is then packaged. Kefir is another fermented milk product. It is originated in Caucasian mountains between Black and Caspian Seas, produced with cow, sheep, or goat milk. The fermentation is carried out by cultures present in kefir grains, which results in production of lactic acid, ethanol, and carbon dioxide. The proportion of grains and milk is around 1 to 20. Kefir grains consist of a white jelly mass containing proteins, lipids, and a complex polysaccharides, the kefiran. It is a symbiotic culture of bacteria and yeast, known as SCOBY. In general, the lactose and alcohol fermented yeast used in the kefir production are Clipperomyces marxianus, Saccharomyces onesporus, and Cerevisiae, and Escherichia, and the bacteria are Bifidobacterium brevi and longum, Streptococcus thermophilus, Lentilactobacillus kefiri, Lactobacillus acidophilus, Lacticase-Bacillus casei, Lactococcus lactis, subspecies lactis, variety D. acetilactis, and species from Leuconostoc, Lactococcus, and Acetobacter. Kefir is produced by milk selecting, evaluating, and heating at 95 degrees Celsius for 5 minutes for pasteurization, cooling to 22 degrees Celsius, followed by the addition of kefir grains or cultures, and incubation at 22 degrees Celsius for 24 hours. From time to time, agitation is carried out to accelerate and reactivate the yeast. After fermentation, it is cooled to 5 degrees and the soft curd is formed. Afterwards, culling and packaging are carried out. In recent years, fermented cream or sour cream has become more popular. It is produced using milk cream obtained during fat standardization. Cream is heat-treated and fermented using mainly Lactococcus lactis, Leuconostoc mesenteroides, and cream is inoculated and incubated at around 30 degrees Celsius until the desirable acidity is obtained, followed by cooling to less than 10 degrees Celsius and packaging. Taste and flavor are characteristics from the starter culture used for fermentation. Fermented cream is commonly used as a condiment or in cooking for its creamy taste and tangy taste. Other dairy fermented products include dahi, vili, and skyr. Dahi is an Indian fermented milk produced with buffalo and cow or mixtures which presents nutritional and therapeutic properties. The cultures used for fermentation are Lactococcus lactis, subspecies lactis, Lactococcus lactis, subspecies diacetylactis, or Leuconostoc species, and Lactococcus lactis, subspecies cranberries. Vili is a typical fermented milk from Scandinavian countries. It presents viscose and filamentous. Lactococcus lactis biovariety long and Getricum candido can be added, result in a typical flavor. Skyr is a typical fermented milk from Northern Europe with high protein and low fat content, similar to yogurt. Cultures used for fermentation are Streptococcus thermophilus and Lactobacillus bulgaricus. The macro trends for innovation in fermented dairy products focus on health benefits, sustainability, and new flavors. The trends were divided into nutritional density and convenience, digestibility and well-being, functionality and prevention, exclusivity and sensory characteristics, and sustainability and ethical sourcing. Nutritional density and convenience is one of the market trends. Many products are high protein, low fat, lactose-free, such as the yogurt enriched with fibers. Other examples are low-fat UAT milk with addition of calcium and fibers, and high-protein yogurt on the go. The use of fiber, probiotics, and prebiotics in dairy products is another trend, this time to favor the digestibility and well-being. For instance, probiotic Minas cheese from Santa Clara Dairy in Brazil and low-fat yogurt with intestinal benefits Activia from Danone, France, are available in the market. The macro trend of functionality and prevention include products with health focused innovation, like good health and immune support. For example, whole milk with omega-3 used to improve brain health from Fairlife by Coca-Cola and high vital hydrolyzed milk protein for children's nutrition by Friesland Campina are available for the consumers. The focus on new flavors, such as exotic fruits, herbs, spices, and is a macro trend for exclusivity and sensory characteristics. Some good examples are Brazilian cheese, such as goat cheese with cocoa nibs and cumaru seeds from Capril do Bosque Dairy, and Cariri cheese with lavender and rose pepper from Taperoá Dairy. Another one is the double cream brie cheese with chili pepper from Castelo. The trend of sustainability and organic products is also a concern of dairy companies. They are changing to and adapting organic, fair trade, and rainforest alliance certificates to demonstrate commitment to sustainability and ethical sourcing. Some companies are producing organic cheese, like Minas Padrão cheese, organic from Brazil. An example of sustainability is Agrindos from Brazil that adapted transparent PET bottles from the packaging of fermented milk brand Lete. Another one is Lactalis Nestlé, which has incorporated up to 30 recycled polyethylene content into dairy product bottles. The future prospect and research directions can be divided into three topics. The first one, merging research areas by the exploration of novel microbial communities for fermentation and focusing in advancements in microbiome science and personalized nutrition. Second, potential application as how fermented dairy can be used in therapeutic and medicinal foods and by the integration of fermentation techniques in plant-based and hybrid products. And the last one, interdisciplinary approach that can be reached with the collaboration among food scientists, microbiologists, and technologists to drive innovation and focus on consumer preferences and market trends to guide research and development. My acknowledgements go to Dairy Technology Laboratory team from São Paulo State University, UNESP, and the research foundations, FAPESP and CAPES, for their financial support. If you have any question, feel free to send me a message. It will be a pleasure to answer you. Thank you so much.
Aqui. Tá funcionando agora? Okay, so we can generate the discussion here, even if Ana Lucia is not here. Actually, I have my opinion. As I mentioned in the beginning, I'm Bulgarian. In Bulgaria, if yogurt is not thick, this is not a yogurt. So yogurt cannot be liquid. Because if you have appropriate fermentation of these two strains, Lactobacillus bulgaricus, actually first Streptococcus thermophilus, then Lactobacillus bulgaricus, they need to do the precipitation and to do this specific structure of the yogurt. And look like the industry just exploring the commercial option and produce these liquid yogurts that actually they cannot do it thick. But that, well, this is my personal opinion, because I have colleagues from Mexico, they say, no, yogurt needs to be liquid. If it's not liquid, we don't like it. So look like a specific test, but traditionally in the Balkan Peninsula, yogurt is considered a thick, you can eat it even with a fork. If it's too liquid, then it's considered a bad quality. But now talking about the cheeses, maybe Wellington here can add some comments about this variety of Minas cheeses that coming in the last years. Do you want to comment something about this? You can use this one. I think it's better because we prove that it's working.
All right. Well, good afternoon, everyone. Well, about the yogurt, it's diverse. And in Brazil, we even have the bebida láctea, or I don't know how to say that, dairy drinks.
But this is not anymore yogurt. This is fermented.
Exactly.
Different name.
Yeah, exactly. But because the talk was about many kinds of fermented products, so about the cheese, I think that there is, well, tomorrow we're definitely going to talk about cheese because it's going to be my talk. And I will talk about microbial interactions in cheese. And now we'll have some people coming and talking about that too. But if you want me to comment on the Minas artisanal cheese, we have several regions in the state of Minas Gerais, each region producing a different kind of Minas artisanal cheese. There are 10 kinds nowadays, plus 5 other kinds, which are called artisanal Minas cheese and not Minas. It's easy to explain in Portuguese, but not in English, because the names are just the same, but they mean different things. So you have Queijo Minas artesanal, which is the classical like canastra cheese, Cerro cheese, and you have Queijo artesanal de Minas. You just change the order of the words and they mean different things. So which are cheeses that are not so traditional in the sense like the canastra cheese, and they can be made with different processes. So this is just a world of cheese. There's Minas, but Ana Lucia showed the cheese from São Paulo, from Caprio do Bosque, which is a famous cheese factory here of artisanal cheese for made with cabra, goat milk. Yeah, it's a whole world about cheese. If we if we decide to talk about cheese, we could stay all day long talking about all kinds of cheese. So,
But it's not fair because you talk about the cheese, but we don't have samples to taste. Yeah. So it's we can actually discuss these things because I mean there is a classification. There's some groups they say the yogurt, to be called yogurt, needs to be Streptococcus thermophilus and Lactobacillus bulgaricus. All rest is fermented milk. But then you do this dairy product with Lactobacillus bulgaricus, Streptococcus thermophilus, but in the same time you have the different, you have liquid, you have very thick, you have same like middle, you have with the fruits, you have with the sugar, you have with the sweetener. So it's a huge variety in the same kind of product. So this is really something that could be discussed in the several way and to find what is the right. But well, according to the scientific opinion, it to be called yogurt needs to be with these two microorganisms. All rest it needs to be called fermented dairy products. And then it's coming another these innovative products that are having non-dairy product type yogurt and type fermented non-dairy product that look like a dairy, because obviously in the normal physiological situation, we can have the dairy products, but then some people have lactose intolerance or need to remove the lactose. But if you think like evolutionarily, milk is for the small, for the babies, not for the adults. And if we even look the ethnical distribution, most of the Caucasian, they don't have a lactose intolerance, but most of the Asian and African descent and Native American descent, they have the lactose intolerance. So then it's coming a casein intolerance. There is another problem. So obviously some dairy products, they need to break down caseins much more in order to avoid these problems. We have in the market all these dairy products without lactose these days, cheeses, milk, fermented milk, because the need of the population it's different, and as well without with sugar, so it's all the variety. So we're going to have some commercial break now, and next speaker will be, I hope it's already linking to the system, it's from Italy, but well, a few minutes for our sponsors that they don't sponsor because they give nothing, they just want their propaganda of their events.
clinica dal produttore.
Sì, è vero che
Allora, le informazioni mi scrivono che
Ciao
sono
Lorenzo,
no.
come stai?
ciao. Bene. What
Bene.
about you?
I'm in University of Sao Paulo working and look like you're in your office.
Exactly.
Or your
But
home.
at home. My office at home.
Okay, home office.
Yeah. You know me.
Okay, next presenter, it's Lorenzo Favaro. You can call him Don Lorenzo. He's a professor at the University of Padua. It's, if I'm not wrong, this is the second oldest university in Italy, right? After Bologna.
Exactly.
So we need to
Exactly.
close Bologna so you can become a first actively working university, oldest one in Italy.
I will. This is my plan.
Pleasure to have him today with us. And even he can sacrifice his evening in Italy because 5 hours more. So now it's 7 o'clock there, right?
Exactly.
And he's a professor at the University of Sao Paulo. It's DAFNAE. It's working normally with biodiesel, bioethanol, how we can use all these waste products to produce valuable metabolites and combustible for our cars. I know him from the time when he was still doing his PhD in partial time in Stellenbosch University, and was really a pleasure to work with him because all this project that he was taking in his hands normally finish with a good success. So now we're going to have his presentation, and after that you can stay with us because we're going to have the discussion session so you can struggle with all the questions that will come from here. So time is yours.
We'll be happy. Sorry, Slavi. I mean, it seems that the presentation is still loading. So I think I already uploaded the presentation half an hour ago, but it's still loading. Now it seems that it's 25%. So I think that we would need 3 to 5 minutes extra. Sorry.
Don't worry. We can extend all the times for you and give you like 3 hours to present if you want.
No, the point is that the slide I uploaded almost 10 minutes ago, but then it is still in caricamento.
Don't worry, we have technical problems sometimes.
Okay. So just
bad news
thank you
for
so much for the
need to
introduction.
talk in English, not in Italian. You understand me?
Yeah, it should be in English.
Okay,
Yeah,
you
sure.
can start.
Can you hear me? Yeah. So sorry, guys, but I mean, I hope now the presentation will be available even using this stream service. %75%.
In the meantime, you can tell us something about you if you want. Except
Sure,
that
I
from
mean, thank you so much.
city of Venice.
Exactly. So thank you so much for inviting me, Slavi. Slavi is the nickname of Professor Todorov. As already Professor Todorov mentioned you, it was really an honor to meet him a long time ago. It was almost 16 years ago at Stellenbosch University. And since that time, we studied something together, and then above all, we had a great time as friends and as colleagues, and then we share our know-how. So I'm very happy to be here. Then, of course, I have studied agricultural sciences at the university. Then I ran my PhD on agricultural biotechnologies, and then I started to be postdoc first, then researcher, and then finally 4 years ago, I was appointed as associate professor. Of course, today, guys, you will not see a lot of food-related stuff about my presentation. I teach 1 out of 4 courses I teach is related to food biotechnology. At the master degree we have on food biotechnology for food science, but my know-how is mostly about on the leftover of food industries to further produce something that could be even useful for the food industry again. I'm referring to packaging and also feed and to some extent food. Now you should be able to see my screen, right? Exactly, great. So the title of my speech is Microbes, Biotechnologies and Biorefinery, where waste streams are processed into valuable products. And before starting my speech, please let me introduce a little bit where I am from. So as Professor Todorov mentioned, actually I live near Venice, in a small village near Venice, but I worked in Padova, and Padova is a nice city in the northeastern part of Italy and is very near to Venice. It takes almost half an hour by train, as well as to other few beautiful cities such as Verona, with its beautiful and very massive Roman arena. And this is actually a beautiful picture of Padova, a small chapel in Padova, very nice, and it has been painted by Giotto, which is one of our most famous painters long time ago, almost 1,000 years ago. And as Slavik told you, Padova University is one of the oldest universities in the world. 1222 is the second oldest in Italy, with almost 60,000 students and a turnover of 0.6 billion euro. It is the second oldest after Bologna, which has been established, they say, in 1064. And it is true that Padova started from a group of students when they decided to leave Bologna, seeking for more freedom. You should consider that at that time, many topics were decided by either church or either the political power. And then this small amount of students, roughly 50 students, they decided to move from Bologna a little bit up towards Venice to study with a much higher freedom. Why? Because Venice was at that time a very strong city, and then they were actually protecting the new students against the church power. And then this is why we started, and then it is the first universities ruled by students for almost 500 years. This is our oldest. Let me check. This is our oldest Palazzo Bo, and this is the earliest permanent anatomy theater in the world. It has been built in the 1594 to let the students studying medicine at Padova University, and they were dealing with autopsies. Its wooden structure has 6 ranks of seats where up to 200 students were standing in the darkness, looking at the body here, the dead body on the table over there. You can imagine that it was not fun at all, particularly during a hot season. Anyway, this is why many human bodies discoveries took place at Padova University. And this is our oldest, actually the oldest botanical garden in the world. It has been built in 1555, and now has been renovated almost 10 years back. And among the eminent students we should cite, we have at least Galileo Galileo, who spent 16 years teaching / studying at Padua University, as well as Elena Lucrezia Cornaro Piscopia, the first woman in the world to graduate. It was almost 600 years ago, and then at that time, guys, women were not even allowed to attend and study at the university. And then this lady was so lucky because her father was a big boss in Venice, and then he helped her to study and was a brilliant student. She would like to study theology, but at that time people said, no, theology is only for church and only for priests. You should study philosophy. That is why she was the first woman to graduate in philosophy, but anyway, in any discipline, and then it was in almost 600 years ago. Okay, then this is the campus where I live. I think that Professor Todorov visited at least twice. This campus is a little bit far from the center of the city. It is in Legnaro. And I'm from Dafnai, which is a recently established department, almost 12 years ago. We have almost 80 academic staff, and then the same number of PhD students, the same number of postgraduate scholarship holders, almost 60 postdoc fellows. And finally, I think that my head of department, since he's very keen on outreach activities, will be happy, and then I can start the topic of my speech. And please, if I'm not clear because my English, or if I'm not clear because I'm too speedy, you are more than welcome to stop me, and then I can try to be a little bit more clear, or to explain better the topics I'm about to deliver you. So as group dealing with the microbiology and biotechnology, in the last 20 years, we have been asked by many food industries to look for potential strategies to process a very big amount of waste into valuable products. And then there is a lot of waste streams that are available in Italy, as well as in Brazil, in Europe, everywhere. Mainly there are sugar-rich, such as food processing, as well as cheese whey, or with high lipid content, such as the waste from the cooking oil industries and the slaughterhouse waste. But also we have byproducts rich in starch. It is the case of rice byproducts, but also potato peels. So when you add polymers to your waste, of course, the challenge is getting higher and higher, and the complexity of the waste streams increase a lot. But it is not still. It is still feasible, and then it is a very nightmare. It is a big nightmare when lignocellulose-rich residues can be considered. It is the case of the paper sludge, or even the pruning after the vineyard. And the real mess is when we have a mixture of complex polysaccharides plus sugars plus water. It is the case of the wheat bran, where only 28% is starch, but also there is a third fraction that is hemicellulose, and 11% cellulose. But also the big issue is the municipal solid waste. In Italy and Europe, we have a big amount of organic fraction of municipal solid waste every day produced and disposed of, and we have a big issue in converting this amount of sugars and polysaccharides into something useful. So far, we just produce two different products out of the solid waste, biogas and compost. But in Europe, more and more companies are considering municipal solid waste as a very promising feedstock to be converted into more valuable products. And then we can speak about it later on during my speech. Now, of course, we would like to address all these waste streams in a biorefinery concept. I think that you are familiar with biorefinery concept. The idea is to have a plant in which we have a couple of inputs in terms of waste streams. Could be just sugar-rich or starch-rich streams, or even lignocellulosic-rich streams. And then, thanks to biotechnological approaches, we would like to obtain a cluster of valuable products. Can be energy, food, feed, or chemicals. So within this scenario at Padova University, mostly in the waste byproducts lab that I'm leading, we are exploiting microbial solution to process such waste streams into either bioethanol, biohydrogen, biogas, so gaseous biofuels, as well as biopolymers. Biopolymers such as polyhydroxyalkanoates that are produced by the strain, and they can be used to develop biodegradable food packaging solution. And then, at least in Italy, there is a big business on it running in the last 5 to 10 years. So during this speech, I'm just sharing with you few spots of what we are doing in the case of bioethanol, in the case of the co-production of bioethanol and biogas from starch materials, as well as in the case of the biopolymers, so the polyhydroxyalkanoates. For instance, one of my latest PhD student dealing with the bioethanol, Rebecca Me, is having a look at a big amount of strains, yeast strains. You know that, actually bioethanol started in Brazil, so you should teach me which is bioethanol rather the other way around. But you know that we need a yeast strain able to process sugars in the case of the first generation bioethanol plants like the sugarcane plant in Brazil into ethanol. Of course, if we are not using sugars, but we are using waste, then the waste is very complex to be hydrolyzed, and then we need to bring to the table robust yeast strains that are able to withstand the inhibitors produced during the pretreatment of the lignocellulosic materials. The big example you have in Brazil is sugarcane bagasse. But also, since sugarcane bagasse or any lignocellulosic materials is quite rich in cellulose or even in cellulose and starch, we need to develop genetically engineered strains to produce the cellulolytic and aminolytic enzymes needed to break down cellulose and starch into sugars. And finally, we can obtain bioethanol. So in the case of Rebecca, we investigated the formic acid as one of the main stressors during the lignocellulosic bioethanol production. And then we ran a big genomic approach, because we tested and then we compare up to 700 yeast strains at least 10% from our yeast collection, and then the other 90% compare with the whole genome sequences available into the literature. And then we found that even small difference in specific regions of their genomes can be linked to a big effect in terms of industrial fitness of the strains. And while we are developing superior yeast strains, of course, we have to deal with industrial microbiology, genetics and genomics, as well as metabolomics. And in the case of the lignocellulosic ethanol production, again, sugarcane bagasse can be a very good example. We have to look for a strain that is able to withstand low nutrients availability, low pH, high and low sugars levels, depends on the process, as well as high temperature. But above all, the strains have to cope with a big amount of inhibitors, such as furans, such as phenolic compounds, as well as weak organic acids. That is why we selected formic acid in the case of Rebecca Me PhD project. But also we would like to develop a superior cellulolytic yeast strains. Indeed, thanks to a big collaboration with Stellenbosch University, we started to first select superior yeast with the best phenotype, and then we decided to start a genetically engineering approach to obtain a yeast able to process at once the cellulose into ethanol, because it was able to produce all the three different cellulolytic enzymes needed to break down cellulose into a glucose syrup. I'm not about to explain all the details. Something that I really would like to point out is that once you get a perfect, very promising cellulolytic yeast or engineered yeast, you think that you did the most. But it is not always like that, because the strain can produce the best ever enzymatic ability to break down cellulose or starch, doesn't matter, but they can lose the industrial fitness, and then the strains can be of very low value at industrial level. So we, in the last 5/6 years, we start evaluating also the metabolic burden of our engineering approaches on the industrial strains we engineered. So to make a very long story, we selected just one strain expressing 4 genes encoding for beta-glucosidases, which is the enzymes able to cleave the linkage within the cellulobios to obtain 2 molecules of glucose. And then we ran the whole genome sequence using Illumina and the mini-ion combined approach. And then we were able to understand where the 4 genes have been integrated and why there was a metabolic burden related to this specific integration. And then this is something that honestly in the related literature, it is hidden, because no one would like to say, okay, I struggled to obtain the phenotype, and no one would like to say, okay, I spent 1 year, 2 years, 3 years of genetic engineering approaches, but then I failed because the yeast was not able to deliver the expected phenotype once tested at the real scale or at pilot scale. But this is something that, in my opinion, in our opinion, should be highlighted more and more, because it will be very helpful for the next wave of genetic engineering approaches. Of course, since 1990s, my big boss, now he retired, Professor Casella, started to work on the process to develop polyhydroxycanoates, which are the so-called microbial biopolymers from food industries waste, such as cheese whey. And then, of course, polyhydroxycanoates are polymers that a lot of microbial species are able to build up to produce as soon as they are starving, because they can't produce any more biomass because they are under oxygen, nitrogen, phosphorus, or sulfur limitation. So they are able to produce intracellularly, and then I hope you can see my arrow with the mouse, but anyway, on the right you can see that the strain can accumulate a very big amount of polyhydroxycanoates within the cells, the white granules, as such that the PHA quantity could be even up to 90% of the cell dry matter of the strain. So PHA can really replace the fossil plastics issue, but if you consider that is only produced up to 1.7% of the total amount of bioplastics produced last year in the world, it means that there is a problem. The problem is linked to the high production cost, and then 50% of the production cost for the PHA is linked to carbon source. So, of course, we decided to look for potential low-cost PHA feedstocks. With a big company, in the last 2 years, we exploited our know-how on producing PHA from lactose. Lactose is the sugar that is usually available in cheese whey. We had expertise on producing PHA from lipids, as well as from starchy waste streams, such as rice byproducts, but also potato peels and also sweet potato residues. So, for instance, in the case of Silvio Proionigo, another PhD student of my group, as well as Letra Parro, we started evaluating rice byproducts and sweet potato waste, and then we started to go the so-called easy way, in which we added a commercial aminolytic cocktail, Stargen, to actually break down the starch content of both rice and sweet potatoes waste, and then the sugar syrup has been converted by a very highly promising PHA producing strain, Cupravitis necator DSM 545, into PHA. Great. It was the first time the PHA production was reported from such type of waste, so we were very happy. And the content of PHA was very high, up to 44%, and then the PHB was very high, more than 5 gram per liter from broken rice, and then up to 4 gram per liter from sweet potato. Great. Of course, we would like to avoid the addition of Stargen, because the Stargen is a cost in terms of production process. So we decided to go ahead with the genetically modified approach, and then we selected again Cinecator because it is one of the best ever PHA producing strain, and then we were able to let it producing two different amylolytic enzymes in order to develop the one-step PHA production from broken rice as well as purple sweet potato. And of course, this is a very long story, because I think that Silvia took 1.5 years to select in silico the best amylases to be considered, and then we dealt with the native as well as codon optimized variants, which means that we selected also which is the best codon usage for Clydis necator. As such, we were able to boost the expression of these specific enzymes into our host strain, and then we were able to select the best recombinant strains, and then we dealt with enzymatic acid and finally with the PHA production trials. And we were very happy. I'm not about to show you all the data, but actually Silvia was very, very excited as soon as he knocked on the door of my office to show me this result. On the left, we have just pinky biomass. On the right, we have no biomass, no microbial biomass, but just a big amount of gelatin. On the left, we had the best recombinant strain, able to process all the starch available into the system into biomass, and the biomass was having at least 60% of the PHA, whereas on the right, Falcon, there is just the wild type strain that was not, of course, able to process the starch available into the system into any polyhydroxycanoate. Of course, then we had with a big publication in bioresource technology, and then we would like to consider a second option to obtain again a low-cost enzymatic pretreatment of broken rice. And then again, Silvia selected the anaerobic digestion because anaerobic digestion, it is a multiple step which has at least the hydrolysis, acidogenesis, acetogenesis, and methanogenesis that is helping in all the residues, the organic waste, to be funneled to methane and CO2. In this case, we selected the hydrolysis step of the anaerobic digestion, and then we wished to process broken rice into a syrup of volatile fatty acid, and then the volatile fatty acid can be converted again into PHA by PHA fermentation. And Silvia I've been at TTU in Copenhagen, and then together with them we developed this novel acidogenesis approach, and then we were able to obtain a PHA from the syrup of volatile fatty acid produced by from the starting substrate, which is broken rice. The third chapter that I would like to share with you towards the biorefinery, I told you the biorefinery should have multiple inputs, but also multiple outputs. Then together with Ameya Gupta, at the time he was my PhD, now is one of my postdoc in my group, we were interested in converting a ripe rice both in bioethanol and methane. So we developed a new recombinant strain able to produce alpha amylase and a glucamylase, and needed to process the ripe rice into glucose syrup, and then we obtain first ethanol, and then the leftover after ethanol production has been used to produce methane out of it. So with Ameya, he optimized the process, and then he was very happy because he proved that our recombinant enzymes were as efficient as Stargen, which is the best ever commercial amylolytic enzymes available in the market. And of course, after the ethanol production, we collected the leftover, and then that is usually disposed of. And then in a biorefinery concept, we decided, no, we're about to use the leftover in a AD, so anaerobic digestion setting, and then we added the inoculum from an anaerobic digestion plant, and then we further exploited the spent broken rice into methane. Of course, I told you that one of the nightmare still in Europe, but I believe also everywhere, is dealing with the organic fraction of municipal solid waste. Why? Because it is full of water, it is full of odors. If you think about that, everyone would like to dispose of the food waste ASAP from their house. And because of being very rich in water, it is running the risk to be managed only thanks to anaerobic digestion and composting. And actually, biogas and compost are within the so-called biocommodities with the lower value. So there's a lot of interest to look for potential alternatives to build a biorefinery from the food waste of our houses, and beside the methane, also collect hydrogen and other biogas, gaseous biofuel, as well as volatility acid that has a much higher value compared to the methane, as well as polyhydroxycanoates and also bioethanol. So we are also interested in anaerobic digestion, and then thanks to Sara Agostini as well as Francesco Morricone, we decided to monitor the anaerobic microbes and archaeal strain that are supporting the biogas from 4 different anaerobic full-scale anaerobic digester, 3 typical of agricultural feedstock in Italy, and 1 typical of organic fraction municipal solid waste. Of course, while we are dealing with the next generation sequencing of their population, we would like to understand which is the content and the composition of the feedstocks. As such, we would like to drive correlation between the composition of the feedstock and the microbial composition of the microbiome we are testing and monitoring. And then in this case, we were able to report that there is a core microbiome. Out of the 4 tested and monitored biogas plants, there were 13 species common, whereas there was a lot of different interaction between either the 3 agricultural anaerobic digesters and the one related to food waste management. But then, of course, I don't want to be too detailed about the NGS because it is not a matter and the topic of today. The main topic I would like to highlight in the food waste biorefinery is that it is already available, at least in Italy, and big number of plants in which the amount of tons managed every year is above 40,000-60,000 tons per year. So we had we have a big collaboration with CESA, that is one of the biggest biogas plant from organic fraction municipal waste in Italy, and then we were able to literally sample their food waste because we needed to understand which is the composition of food waste, if this composition changes along with the time, along with the season, and along with diets of the people. And we were able to sample this food waste, and then we were able to prove that it's possible to obtain ethanol out of it, again for the first time, but also we proved that it's possible to produce also biopolymers and hydrogen before sending the leftover towards methane and composting application. The last chapter of my presentation, again, Professor Todorov asked me to give you a few spots and then hopefully to get your interest and then to have a couple of questions after my speech, is that we can even produce something very important for the food industry, which means biodegradable packaging out of CO2. Indeed, my group is involved in a couple of European projects. This one is ACT, which is all about capturing CO2 from biogas into succinic acid, that again can be used to produce bioplastics, but also into PHA. So the overall idea is to look for novel approaches to capture CO2 emission, either from biogas, either from the wineries or either from other industrial processes. And CO2 can be captured into bioplastics. As such, there will be much lower GHG emission inputs. So we are working with the Cinecator, again, one of the most important PHA producing strain, but also with cyanobacteria such as Synechocystis. And then we are testing the best condition to grow both strains at lab scale, but also at a large scale towards then the maximization of PHB, so one of the most important PHA production. For instance, with Paolo Costa, who recently graduated as PhD in my group, it was really last week, we had a nice idea. The idea was to, again, make use of the anaerobic digestion to process food waste, in this case was melon waste, into a syrup of volatile fatty acid, but also hydrogen and CO2. So with Paolo, we developed this two-step process, and then we, thanks to with a collaboration within the University of Coruña in Spain, Paolo spent there almost 6 months, and then we were able to establish a two-step process. The first one, an anaerobic reaction, an anaerobic reactor, where CO2 and hydrogen have been produced from the melon waste, and then CO2 and hydrogen have been feeded into the autotrophic PHA production here, into the fermenter. And here we proved for the first time that it's feasible to obtain PHA from a mixture of CO2 and hydrogen obtained from a food waste. Such PHA is under investigation in terms of mechanical and purity assessment, because then we would like to develop the first prototypes to be tested for food packaging in my lab. So I think that after 45 minutes, I hope I was able to deliver you a few spots of what we are doing towards the biorefinery approach, where actually a couple of food waste streams must be processed by biotechnological solution to obtain a cluster of chemicals, energy, as well as food or feed. And of course, at the end of my speech, let me acknowledge all the people, at least the most important groups I had the honor to work with, and together with the companies and the institution that founded the group so far. And of course, I would like to acknowledge the microbodies team I have in UniPD, because without them, I won't be here. And then it is really a pleasure to grow with them and to be pushed by them towards very exciting future research outputs. I thank you so much for your attention, and then I will be pleased to answer to any question about my speech and also about any doubts or ideas I hope are was able to rise from the audience.
Lorenzo, can you hear me?
Sure.
Okay. Thank you very much for the presentation. Now, my greetings to Zalia, your boss, ex-boss, how she is to your boss, and to my
Colleague, yeah. I can hear you. I can't hear you.
Now it's working?
Sure.
Congratulations, Professor, for the wonderful presentation. My questions here is, in Brazil, are using
Lorenzo, can you hear me?
Sure.
You can. Oh.
I don't know, this one is working.
Sure.
Yes. I said, like Brazil here, they are using sugarcane, like waste products from sugarcane to produce bioenergy or maybe any substance that can use in the agri product in the soil. One, is there any rules that may be given to using these waste products, like agri industrial products or municipal waste product or agri product? Like this product, using this product, like can produce emission, maybe during the process. I don't know if there's any standard rules that apply to this using these waste products.
Yeah, thank you so much for the question. If I understood well, you pointed out the fact that all these valorization strategies must be considered also by a life cycle assessment and techno-economic assessment. Because of course, I agree with you that if a waste is available, it's a pity to landfill it or to burn it. Because in Italy, actually, only 10% of the waste is currently landfilled. 25% is burnt to obtain heat and energy. The rest is either recycled or processed into biogas and compost. So in every biorefinery approach must be assessed considering the life cycle assessment, and also the environmental inputs and outputs the biorefinery is delivering. And at the end, we should be, of course, with a GHG, or with an environmental impact negative, which means that we are saving the environment from additional pollution or additional damages. I hope I understood well the question. I can't hear you, Slavi. I can't hear you, Slavi, sorry.
Aqui, som, teste.
Now the colleague I'm able to.
It's with me.
Sure.
Now it's work.
Sure.
Okay, now I'm talking about something else. Do you think in the near future we'll be really able to recycle and to use all this waste? Because in these days we have several projects, we have a different idea, we have different approaches, how we can use practically everything, anything. But again, realistically, do you think we will be able to use the older waste, or we are still in the infant stage of these projects?
Yeah, great question. I think we should consider honestly country by country, because I'm familiar with the Europe, and then mostly with Italy, and then even the latest assessment in terms of recycling share within the food waste and the food processing waste is highlighting the fact that Italy is on the top of the list, not because I'm from Italy, but I told you 75% of food waste is currently recycled or converted into valuable products. But I can tell you that Greece or Spain or even Norway is the other way around. So they are used to either landfill or burning the majority of the food waste. So I agree with you that we should select a number of valuable products to be obtained, and then we should invest money in terms of European Union, at least, to say, guys, after scouting the latest and hottest biorefinery approaches, we should select A, B, C, D, and then the rest will be in the next wave of biorefineries. Otherwise, we are losing time and money just to select. To go ahead with every approaches, because I agree with you. Everything looks nice, but must be applied at higher scale or at industrial scale. This is the big effort.
So we still have a lot of work and
Sure.
work to do. As Nelson Mandela, it's a long way to freedom. It's a long way to really reuse all the waste.
Exactly.
Any more questions? Well, I have a question.
Do you know which are polyhydroxycanoids?
Say again?
I was addressing a question to the students. Do you know, before my speech, that polyhydroxycanoids can be used for food packaging?
Well, look like it's a new thing for them.
Okay.
So this is why my next question: when are you coming to Brazil?
You should invite me first. You should invite me first.
Well, the carnival is coming. You can come for the carnival and then giving some presentations here. Just ask Marta if she will agree you to travel far away.
We should make a plan for it.
Okay. But, well, thank you very much for your presentation. We're going to have a general discussion from 3:15. So if you can be logged again to the system or stay around for a few minutes later, if maybe appearing some questions, will be very nice. If you decide to have your pizza and enjoy the nice pizza and wine, we understand because it's time for dinner. But well,
I will be on, but then of course, if questions will be addressed, I will be pleased to answer. Yeah.
because we're going to have in a few minutes presentation from our director of the postgraduate program, giving some information about opportunity for master and PhD studies in Sao Paulo University and our faculty. So maybe you can send some of your students here as well. Let's see. So you can win some information. But anyway, we're going to have a couple of commercial break. As I say, commercial break without commercial profit because we're doing it for free. And after that, at 3 o'clock, we're having our director of the post-graduation program to present our changes that we have done in the last couple of months here and what's the opportunity for do the master and PhDs at our university and our faculty. But again, thank you very much for your participation and maybe see you in the next minute and depends of the how the connection will work. Thank you very much and see you soon.
See you soon. Bye-bye.
Alô, 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 som. Hello, hi everyone. My name is João Paulo Fábio, and today I'm going to speak a little bit more about our new graduate program in integrated food systems. Sorry about that the presentation is in Portuguese, but it was made for the Brazilian students, but I'm pretty sure that talking English, some foreign people, they can understand it. So our new graduate program, it's a fusion of 3 old graduate program. One that is called this one here, that is from the Engineering University in Pirassununga. The other one that is from Food Science and Technology from Exalc, and our program system, our ex-graduate program. Just going back a little bit, so a brief history. So we need to fuse 3 different and old food science graduate program in just one. So we are now calling it as a food system graduate program. And what is the food system thing? So for the researchers, we need to study how the food they are produced, how they are distributed, how they are processed, how we can develop new foods, how we can sell it, how we can prepare it, and how we can deal with the food byproducts. And everything is connected with the human being. So human being, they consume food, and these systems, they can study how the food components can interact with human beings. So our new graduate program, there is only one concentration area that is called food science, technology, and engineering. And we have some specific here about the master's and the PhD. And now we are going to have two specific tests, one in each semester. So the students, they can apply, and they need to run this test, and maybe this test will be FUVEST will do it. We'll do the test for our new graduate program. And these are the 4 research lines that we have. So we have the development and innovation of foods and beverages, the development and innovation of process, the food safety and quality during the whole food system chain, and the relationship between food and health and human health. So these are just some projects of each research line. I'm not going to translate it for you, but afterwards you can have it. I can send you. So this is for the research line 2, the research line 3, and research line 4. And now we have this website that is really easy. You just go and just write straight ahead in Google Sites and sites.usp.br and Alimentos. There is no English version yet, but we are now translating it to English and Spanish also. These are the contacts. So me, Professor João Paulo Fabi, I am the coordinator of the new program, and Professor Alessandra Lopes de Oliveira is the vice coordinator of the program. So I am from the Faculty of Pharmaceutical Science, and Alessandra is from the School of Engineering in Pirassununga. So if you need if you have any doubt, you can contact me. And sorry about the presentations in Portuguese, and but I hope everyone could understand a little bit more. And whatever you want, you can just send me an email. Okay. Thank you, Professor Slavi and Professor Wellington, for the opportunity. Yeah. Do you have questions, guys? Yeah.
When the applications will be available for the new program?
Yeah, tomorrow we are going to have our meeting to understand when we are going to have the first test, but I presume it's going to be middle September this year. Okay, and we will try to do it maybe in the middle of each semester. And of course, just to clarify it, and the test, when you apply for the test, you will choose your specific area. So if you are not a engineering, you are not going to be able to answer the engineering questions. But if you are a pharmacist or a nutritionist, there will be some specific questions for the area that you are going to sign.
I want to ask something and then I can leave. Is the post-graduation program open for the foreigners?
Yeah, it is open for the foreigners, but we are now trying to figure out how they are going to enter in the graduate program, because the test will be available. This first test will be available only in Portuguese, but we are now going to understand how we can do it for the foreign students. Maybe a specific test for them. This is your question. Yeah, we are the things that we have. We can't offer the same test in different language. There is something that it can't be done right now, but it can be done in the future. But if any professor, or we have some students that they are from the outside of Brazil and they are not native in Portuguese, so we are trying. We will have to understand how we are going to do with these people, the Spanish language, the English language. Okay.
I will make your life very difficult, because another question: when the students from outside come, how they can benefit from the grants for the bursaries from Brazil? It's an option, or they need to rely on their own funds?
For the Brazilian CAPES and CNPq, there is no difference between foreign people and Brazilian people. They are going, the students, they are going to receive the same scholarship. But the thing is that we don't have funding for foreign people, foreign students, to maintain themselves here in the University of São Paulo. The graduate program doesn't have it, but the University of São Paulo has some calls for foreign people. So the University of São Paulo has the graduate program. No. This is another thing, because depending on how we are going to apply the test for the foreign students, we are thinking about not, how can I say, they will not need to pay a tax. And this is a common question, because the foreign people that they come here, they think that they need to pay for a bench tax. And University of São Paulo, it's a public university, so it doesn't exist this kind of thing. She asked how many space spots there are for students. We don't have the maximum, and we don't have the minimum. The thing is that we have the number of scholarships from CAPES is not high. So just approximately 50% of all of our students, they have CAPES scholarship. Just 50%. The other 50% is from FAPESP and from CNPq. And one thing that we are now trying to do is, if a student has a scholarship approved from FAPESP, we believe, we understand that this student and the project has already been evaluated. So for these students, they can enter the graduate program directly without being tested by FAPESP. And this is a nice thing, because as we all know, FAPESP, it's a very strict and very difficult scholarship. So if they have already been evaluated, there is no point that we will also evaluate them. So they just, the student can only show the English proficiency test and adopt resume or whatever it was taken. It's a nice thing, yeah.
Maybe I can add something. Well, you say that technically it's no limit how many students can enter the program. I think only the limitation is the fact that the professor can take certain limit of the student on his own. So this is actually the limitation, but this number multiplied by all the professors of the program is actually quite high. So technically, we cannot have such a number of the candidates per professor. So credited, so many credited professors in the program, more or less. So 35 professors, so it's mean 350. This number never been in the history. So technically we have the spots, and again, to encourage the students to work hard and to try to have the grant from faculty or from industry. So this will facilitate the financial part and be more independent when they do their studies.
So we have a lot of spots, and the things that you can enter in the website, and maybe in 1 month we will have more information about the selection criteria. Okay. Any other questions? But I am also available in my email if you want something. No more holidays. Yeah, I'm just going back to work. Okay, guys. All right. So thank you very much, and I hope to see you all around.
Thank you very much. That's really helpful. So now the bottom line price of anniversary, because it's easy to start, and better they already include the amount of the support, so it's a good one. Well, now it's coming to the general discussion. Today we had different presentations from different subjects, starting from antimicrobial properties. We went to the pieces. We had the dairy products with Anna Lucia. We have kombucha and other fermentations from Tony from New Zealand. Luciano was talking about selection and technological properties of different beneficial, different technological property of the starter culture. Lorenzo was covering some parts of the technological properties of the bioconversion. Now, what do you think? Where actually it's a more valuable part of working? What you see you vision of a young scientist? Because sometimes ago I was telling that actually the future of the science is the students, because the professor is already soon will be retired and go to spend his time on the beach, and students need to work and get the new professor. So what do you think? What part is more excited and more interesting for you to go? I want your opinion. Because if you don't have any questions or opinion, just take one white paper. We're starting the test. Already, some of you I know you work with some of these topics. So, have you think to change something? Do you have some new ideas from this presentation? What can they explore more? How do you see the change in new projects? You can discuss what do you think you useful.
Hello. I try to speak in English. I really like the lectures, and I have a question for Professor Anthony from New Zealand, and for you, Professor Slav.
Well, Anthony is already sleeping, so I need to answer.
Okay. He said that to isolate LIB from kombucha or traditional food, fermented foods like indigenous food, the idea is to take sample every 48 hours during the fermentation process. And during this process, the composition of bacteria and metabolites change. But sometimes it's difficult or impossible to do this, to collect the samples during 24 hours or 48 hours. If only the final product is collected, is there a high chance of losing the LIB that produce bacteriocins? I mean, do you know if LIB that produce bacteriocins are more predominant at certain point of the process or not? It's available in the final product, in the
Well, I can try to answer this question. It's working. No, now it's working. Now the point is something more specific. Tony already mentioned the question logical composition of the process. We need to collect this time because going to the sauerkraut is a very coming after that one disappearing. I think olive why you need to check in the different moments. And now it's working better or not? So this is the point, because since the microbiological composition of this fermented food products is changed all the time, so we need to take several spots, because if you take only in the end, you're having this moment in the end. Very often the cheese fermentation is not such a big variety of microorganisms, and they're more or less stable, the dairy products. But different plant fermented products, they change their composition. So this is why we need to take several samples in all around the time to order to be sure that we will pick something more interesting. From another point of view, we need to pay attention on another interesting point. If you look for specific group of microorganisms, we need to enrich them. So we're taking samples and we're enriching the samples to give the force to grow this group of microorganisms that we want. Because obviously in let's say kimchi, fermented cabbage day in China, Korea, Vietnam, no, Vietnam not, Korea and China more or less, in Taiwan maybe. So kimchi, it's can have some spoilage, can have some bacillus there that we don't want them. They have several lactic acid bacteria. They have acetic acid bacteria. They could be a spoilage, so they will give this sour taste of the kimchi that we don't want, like a vinegar test. But this, it's a point. They will always exist, this additional microorganisms. It's not a laboratory pure culture, a control condition. It's a natural fermentation. And then we can use some additional components in the isolation media, so we can actually force to select only what we want. Then the people that work with the bacteriocins, they know we're using this as a culture level method when we pre-select the microorganism that's producing antimicrobial. So we have adding some additional step in the isolation process that we can actually focus on the specific group. If you want to have the yeast, you add some antibiotics, so you can kill bacteria. If you want bacteria, you add antibiotics that kill yeast. So in this way, you can actually modulate and see what you want to isolate. If you want to have ecological study, you need to know what is all the bacteria that's in the product. This is a different story. But if you're looking for specific bacteria producer of some specific metabolites, you can actually modify the media, you can modify the protocol, so you can push the entire process on the direction that you want to isolate some specific microorganism. Let's say if you want to have some vancomycin resistant, if you want to check if the products could be dangerous because carry some vancomycin resistant, a microorganism at a very high level of vancomycin, and you kill all rest, and you have only this that are resistant. So you can always modify the way that it's objective of your study. And this is why Tony say every like 12 hours or even depends because it's a fermentation process is dynamic. Everything changes. Even the yogurt, the real yogurt, how it works. First, Streptococcus thermophilus start to grow. Lactobacillus is almost not growing in the beginning, and then Streptococcus reducing his growth ability, and Lactobacillus bulgaricus start to grow. So if you take in the beginning, you detect predominant Streptococci, and if you take in the end of the process, predominant Lactobacilli. But you want to know what is there, so take samples more frequently, and you can see what do you have in fact.
Thank you.
More questions?
He made mention of addition of salts in the sucrose. So I'm thinking of how can someone prevent contamination of maybe growing of malt along the line, because by that point he said after addition of salt, then it goes to fermented culture. But I'm thinking of controlling the growth of malt along the system.
Well, in the Balkan Peninsula, we have expression that for every pain we have a plant, medical plant that you can cure every pain. Same thing in the microbiology. For every bacterial group, we can have a property inhibitor. So when you want to inhibit the growth of the fungi, molds, and even yeast, we use some, I think was actidion was that we add in the growth media. And actidion actually inhibit the growth of the molds and yeast. So this is way, let's say, this Bulgarian beverage that I was mentioning, boza, it's very rich on yeast and lactic acid bacteria. But if you want to isolate lactic acid bacteria, you add some actidion to the media. So you actually inhibit the growth of the yeast and fungus. So in this way, you can control them and they're not going to grow, and you have growth on your lactic acid bacteria. As I mentioned, for the lactic acid bacteria, you can use some antibiotics, appropriate antibiotics. So you can have only the yeast, depends what is your objective. But always you can use some additives, some antibiotics. You can play with the anaerobic, aerobic condition as well, because in this way you can control one or another group of microorganisms. As well, adding the salts. Enterococcus was much more resistant to salt than some lactobacilli. And if you know that you have enterococci and lactobacilli in your product, adding the salts, you can actually reduce the growth of some lactobacilli, and you can predominantly isolate enterococci. So very often the error that I can see in the papers, people using some specific conditions that they tolerate the development of one or another group of microorganisms, but after that they claim that this is the microbiological composition of the product. No, it's a microbial composition in this specific condition when we tolerate some specific group of microorganisms to develop. This is the reason when we use the sauerkraut, we use in the salts in order to prevent, because some of the pathogens actually are much more sensitive to the high salt concentration compared with some lactic acid bacteria. And this is the way to preserve the product of development of some spoilage. And I think we have the question from the online. Oof. Microphone.
All right. First question, what are the most significant hurdles you have encountered in the process of purifying and characterizing new bacteriocins from natural sources?
Well, it's not easy. Actually, when I'm teaching about the bacteriocins, I like to show the painting of Mona Lisa and asking everyone, I agree this is the art. Everyone agree. I mean, if I show maybe Picasso, will be some different opinion, but Mona Lisa, everyone agreed that Mona Lisa of Leonardo, it's an art. Purification of proteins is an art as well. There is no recipe. There is no protocol that we can follow when we can have the final response. So the purification of proteins is a very complex process. We need to know very well biochemistry, and we need to try several options to see what's the appropriate condition. In general, we do the ammonium sulfate precipitation, and then we use the several methods to separate this protein based most probably on the hydrophobicity, on the electrical charge, or the size. But we need to have this appropriate column, chromatographic column. The problem in the last 2 decades, people detect the gene and everyone is happy that we have the bacteriocin. No, no, because the gene is there, gene is part of the genome, but we don't know if it's expressed. And very often we can detect more than one gene, but which one of them is expressing? So we need to have RNA level test to prove which bacteriocin is expressed, to know which bacteriocin we have, or we need to really purify this protein. But this is a protein chemistry. It's a completely different area, and it's a complex process of different methods for separate the proteins and to have them as a pure protein. Even in the end, you think you have pure protein, you run the PCR, you show, not PCR, HPLC, you show pure peak, and then you do the mass spectrometry, you see that actually it's a one in the top of the other one. So you still need to go for a different method to separate, but several approaches, including chromatography based on the hydrophobicity, based on the cation-anion exchange, chromatography based on the molecular size, could be an option and could be giving success. Very often, this is combination of different methods. It's not only one. And it's really hard to do the purification. And this I show very high respect for the people working in the protein chemistry, because it's not a protocol. PCR, you have a protocol. If the PCR works, you can do it. You can repeat it, and not a big deal. Well, if you need to optimize to design the primer, is different story. But already having a primer, having the condition is just repeating. But protein chemistry, it's a combination of knowledge and experience and art to find a appropriate way to have to the final protein as a pure substance.
The next is 2-in-1. I would like to ask about the biodiversity of microorganisms and the lack of standardization that occurs in the production of traditional fermented foods, especially kombucha. Could you comment a bit on why these foods and beverages are considered safe despite the presence of pathogenic microorganisms?
Well, technically, to be commercialized, they're not supposed to have the pathogens organisms. If they have pathogens, they're not going to pass the safety assessment and not supposed to be liberated. If we have the industrial production, they have the control and they're supposed to have a really safety assessment and be sure what they have. Moreover, several of the kombucha products in the market, they're sterilized. They're pasteurized or sterilized. So they're supposed to reduce the number of the microorganisms. But this actually compromises their beneficial properties, because if we pasteurize, if we reduce the number of the microorganisms, we're obviously reducing their bioactive viability. So another point, if we have the kombucha from non-certified sources and kombucha produced by the smallhold producer and sell illegally, then I cannot guarantee that these products could be safe. In Brazil, we have Anvisa that control all these things and try to put everything in the safest way. If they discover something going not very clear, they will recall the product and will even take a license and then going to authorize the sale. But several people think that homemade product is always good. Not always, because if it's produced in the wrong condition and not with appropriate sanitary regulation, rules, etc., this can contain some pathogens, bacteria, and then can be dangerous for the consumption.
What are the beneficial effects of kombucha with approved health claims? I would say the approved health claims.
Well, kombucha, it's for more than, I don't know how many thousand years, been produced in the Asian culture. Traditional medicine recommend them for the several diseases that can, but again, some clinical trials, I'm not aware. We need to ask Tony and some other colleagues maybe to contribute to this answer, but the problem there, Tony is not online. But again, traditional claim, this is not clinically proved. I mean, I say the Bulza, the Bulgarian cereal-based beverage, have traditional claim that help in the tuberculosis, help in the case of influenza, helping the lactating woman to have more milk. Well, this is the traditional claim, but I mean, the clinical trial was not proving practically none of them. We're having evidence to know that some metabolized part of this drink have this effect, but clinically, no one was actually proving this claim. And this is a difference between the Western medicine and the traditional medicine. Traditional medicine is something very good and can be complementary treatment, can help, but again, some claim need to be proved and to be ordered to recommend this as a real clinical treatment. So this is the difference. Even the cheeses, several cheeses have the bioactive peptides. Okay, this is good excuse to eat more cheese, but this is not a good excuse to believe that cheese will cure our disease. I mean, some of the bioactive peptides in the cheese show that can reduce the blood pressure. But this means we need to stop to take pills for the blood pressure and eat more cheese? Obviously not, because if they have the clinical trials and climb, okay, this is a different story. But we're not supposed to mix traditional folkloric medicine with really evidence trials and proof that effect of some beneficial metabolites and microorganisms. This is the reason in several European countries it's not authorized to claim probiotic properties on some dairy products because we don't have clinical trials that can prove this. So I cannot put something that will cure your disease and you will buy it and eat, and if I don't have a real proof of this. So again, this is the protection of the client, because could be some speculations and even some negative effects. This is good, but please enjoy, but listen your doctor as well. More questions? Or you already? Ah, yeah. Okay, you can have the last one. Well, as I know, some Asian countries, they already have the products that contain the lactic acid bacteria producing of GABA, and they claim them as good probiotics. And even they enrich some of the chocolates even with GABA in Korea. But in the same time, I'm not aware of other probiotics that are commercialized. We're going to have the presentation of Mince Leong. I think it's on the third day of course, and she will talk about the probiotic as neuroprobiotics. So actually how the probiotics can interfere with our nerve system and can improve even in some cases diseases like Alzheimer's. So obviously she will give more details on your question, because some of these other molecules produced by the probiotics and affecting our nerve system, they are already well explored, some patents and some commercial applications. So we'll have something more details on this in some of the coming sessions. And if you don't have more questions, I suggesting so we can stop for today. Thank you very much for your presence. And please fill the presence list that Gabriela was having printed for the people that are here. Everyone that is online, we sent on the chat system, and we will send now again. So you can fill this form, and this form will be served as the witness that you've been attending the course today, in order to receive your certificate later by Gabriela, that is the PhD student in our lab and helping a lot in the organization of all this process. So thank you very much again for your patience today, and see you tomorrow at 9 o'clock. Okay, thank you.